So, good morning, everyone. Can you hear us?
Yes.
Yeah.
Perfect.
Hello.
I guess we are already more or less complete in terms of participants, so I think we could start.
Yeah.
Alrighty, so good morning, everyone, to this 2 days of PULP training. Over the next couple of hours and the whole next day, we will deep dive into several different topics about hardware and software development with PULP. But I guess before we start with the technical meat, let's have a quick introduction around, at least a very short one, so the people that are not from ETH know who we are. So let's see whether that works with the slide. Yeah. So actually, it seems like my webcam is frozen, but I have to deal with that later. Maybe I'll start with me. I'm Manuel. I'm a PhD student under Luca Benini that started about 2.5 years ago. And yeah, I guess most people here already know me. For the ones that don't, I mainly work on smart wake-up circuits, so VLSI design of circuitry that does wake-ups on sensor data processing with a certain kind of machine learning, but I'm also quite involved in PULP SoC development and chip tape-outs, besides doing occasionally firmware development and system-level design of hardware demonstrators, PCB design, etc. That about me. I guess Robert can introduce himself.
Hello, I'm Robert. I'm also a PhD student at ETH Zurich. And together with Manuel, we are the maintainers of the PULPissimo platform. I mainly do research with real-time system on the software and also on the hardware side. That's basically.
Yeah, all right. I guess since we are way too many people for everyone to introduce themselves, we skip that part and directly head to the introduction about what we have planned for this training. So for day one, we are going to start with a deep dive into the SoC architecture of PULPissimo. Actually, not only PULPissimo, but also PULP, because they share the same SoC infrastructure. Then Robert will introduce you to the software environment that you can use to program and work with PULP systems. And we will continue with the RTL Development Flow, how you handle IP dependencies, and how you can, in the end, build the RTL simulation platform, and some tips and tricks on how you can debug hardware and software using the environment that we provide with our PULPissimo platform. Day two, we will mainly talk about we'll start talking about the FPGA port, how it differs from the ASIC version of PULPissimo, and give a little overview on the IP landscape that we have with PULP, and just make you familiar with what kind of IPs we have available, so you can reuse instead of reinventing the wheel when you design your own IPs. Then there will be some two larger exercises. One will be about the integration of a complete custom IP. We created a dummy IP that you are supposed to integrate yourself using the tools that we will introduce over the first day and also the second day. And the second exercise on day two will be about the PULPissimo memory layout modification. So how you can change the banking factor, how you can change the how you can add additional private banks to the SoC, and also how you have to modify the linker script for the C runtime to properly work on the modified memory layout of the SoC. During the training, I mean, we try to make this as interactive as possible. So if you have questions, please interrupt and ask. I mean, we cannot possibly know where people struggle to follow or where things are unclear. So in case anything troubles you, you don't understand something, or you want to know some additional thing, just interrupt. And yeah, I mean, if the discussion derails, of course, we might force to proceed, but still we try to make this interactive. So please interrupt us if you have any questions or notes. I mean, we don't know everything. I mean, we're not the ones that designs PULPissimo. Just happen to know quite a bit about it since we're using it personally. But I'm sure there are people in the call that know more on certain aspects, probably some of you about every aspect, but yeah, we're the ones that happen to have to do this training. So yeah, please also interrupt us if you have any notes or correction on what we just said. So the first part that I want to start with is kind of a quick overview on system Verilog atrocities. I thought I'd put this topic right to the beginning because I have the highest chance to reach the people before the attention kind of drops. So this will be about some coding style, actually not coding style, but system Verilog misuse that some of you might think is a bit opinionated, but I guess some of the topics are not at all opinionated, but just misuse. And the reason that I put it right in the beginning also is to maybe, I mean, my hope is that the code that we will write in the future will have less of those issues that I'm just going to introduce to you right now. And I guess that some of the coding style that I will talk about happen to be used because tool support in the past for system Verilog wasn't as good as it is right now, and unarguably still isn't perfect today, but way better than a couple of years ago. But still, I would urge you to not do some of the mistakes that I talk about. So the first and probably the most annoying one is importing into global scope or into the compilation units scope. So if you import your types in before the actual module declaration, not only is that illegal system Verilog code that just happens to be supported by most tools. I mean, if somebody knows better, you can correct me, but I actually checked the specifications and I couldn't find that this is actually allowed by the Bacchus Naur notation, but maybe I'm wrong there. But regardless whether it's actually legal or not, the issue is always the same. If you import your types, your parameters or constants into the compilation unit's scope, you will basically pollute the whole scope of your project while compiling. The problem is that this compilation unit is tool dependent. Some tools will compile each system Verilog file in its own compilation unit, and you will have way less naming collisions. Other tools like Vivado by default use a global compilation unit for all system Verilog files in the same project, and you will have naming collisions all over if you import, especially if you .star import into the compilation unit. So a way better way to do it is to just import it right after the module name. This is actually legal system verilog syntax. I think since the very beginning. I think Verilog 2005, or actually system verilog already allowed that from the very beginning. And I mean, if you import it right here, you can already use the constants in your port list, and everything works as expected, with benefit that you don't pollute the compilation unit's namespace. It would just be imported in the scope of the module and nowhere else. And if everybody does that, then we would have way less troubles trying to compile the PULP SoC with tools that have a global compilation unit. The second problem is the usage of parameters that are actually not parameters. So if anybody wants to add a reason why you would want to do it that way, then I'm happy to hear it. But I mean, the issue with that is, as you can see in this dummy example, the BE width is actually a derived constant from a parameter. It could be changed externally, and skimming through the PULP SoC code, it happens regularly that people don't pay attention well enough and override parameters that should not have been changed, and does a way better usage of it. I mean, it doesn't matter if you declare the parameter up here or down here. Actually, I see there's quite a bit of, oh wait, let me use the laser pointer, maybe it works better. Yeah, better. It doesn't matter whether you declare the parameter up here or down here, it will be something that could be overridden externally when you instantiate the model. So if you want to have some constant that's derived by parameters, actually use the keyword for it. So the keyword would be local param. If you use this parameter, you can still derive it from something else, but it can no longer be changed externally. And it's just a nicer way to do things. And I think this is also legal syntax since Verilog 2005, and almost every tool nowadays supports having local parameters also in the port list. I know that there were some tools in the very early days that didn't support this syntax, but I haven't encountered any issues since. So, yeah. Then another maybe less known thing, elaboration system tasks. I mean, if you actually declare parameters, it's always a good thing to document what they're doing. But also it's important to document the legal input space of your parameters, because as we will see later on, there are a lot of parameters throughout the PULP code base that seem parametric, but actually are not to be, or are not supposed to be changed, or only have a very limited legal input space. So you cannot just put any arbitrary value there and expect it to work. So a good thing would be to actually document what's legal, but an even better way would be to use system verilog elaboration system tasks. So that would be that part down here. See it over here. So I mean, you can basically ignore the expression I have in this if loop. That's just some bit magic that tests for power of 2. The important thing to note is that we have a generated if statement and an error message down here if the expression happens to be true. And if you do it like this, outside of any initial block, the cool thing about this is that that's supported not only by your simulator when you're actually simulating things. This will be by System Verilog standard 2012 or newer, be checked during elaboration. by your simulator, but also by the synthesizer. So Synopsys supports this, Vivado supports it, and Questa supports it as well. I don't know about other tools, but I mean, I also checked. Verilator supposedly supports it, but I didn't check personally, but at least they write that they do. And it's just a nice way to check that your parameters have an input that you're expecting, and you can enforce the user to not parameterize your modules the wrong way. Yeah. So then we have includes. So this goes a bit back to the import into the compilation units scope we had in the beginning. It's related in the sense that include paths are most often global to the whole project. And if you use extremely generic names, both for the include file name as well as defined within that system verilog header file, then you will end up with naming conflicts. So please don't use generic names, but prefix all your headers and defines with maybe the IP name of with the name of your IP, or just take other measures so you can be sure that there are no naming collisions where they don't have to be. Then about generate statements, I still see this kind of thing quite a bit in the code. So that's not necessary at all to write it in that manner. It's actually redundant to use the generate statement is optional since Verilog 2005. You don't have to write it, and since you don't have to, it's just additional verbosity that you don't need. Also, the generate variable can be directly declared in the generate for loop. But even more important, I'd consider the usage of labels. So please always label your generate blocks. Otherwise, the hierarchical names of whatever you instantiate within the generate block will be tool dependent. It will depend on how the tools will automatically derive the name from the generate block, and most of the time you don't want that. So always label your generate blocks and try to avoid additional verbosity by getting rid of unnecessary generate regions. Any comments or opposition to what I just said, or questions?
Maybe just a small addition. Thanks, Manuel, for highlighting this. We actually try to follow a coding guideline put forward or maintained by Low Risk. I'll just post it in the chat. But that's highly recommended reading for anyone who regularly works on hardware. It really helps you write hardware that is widely usable.
Yeah, thanks a lot for that addition. It's actually something I wanted to say, but completely forgot. So yeah, there is the low risk style guide on how you should develop RTL using System Verilog. I guess some of the style guides is just a matter of preference, and as it indicated, style guideline, but there are also many tips that do not only relate to the style that low risk wants to enforce their RTL developer to use, but also some tips on how to develop stuff that actually avoids issues like simulation and synthesis mismatches. And yeah, just tries to avoid common pitfalls with System Verilog. Any other comments or questions? No? Okay. Then after starting with that, yeah, direct stuff, let's jump on an overview on PULPissimo and PULP SoC. So this will be a pretty detailed overview and code walkthrough of PULPissimo and PULP SoC, but yeah, I mean, this will be probably a bit of a longer monologue, but I think it's crucial for everybody that's not that used to PULP SoC to understand how it works, how the module hierarchy looks like in order to work with it. And if we start right from the beginning, I mean, probably everybody that already had a look at PULPissimo on GitHub saw this illustration, and it gives a good overview on how the intent of the designers of PULPissimo, what the intent was. So PULPissimo basically is a single core microcontroller that started from the Pulpino project, which was it's basically the successor of Pulpino, and it's an SoC architecture developed around our RISC-V cores. I mean, they used to be our RISC-V cores. Nowadays, both the cores supported in PULPissimo, RISC-V and formerly Zero RISC-V, have been donated to other organizations. So Zero RISC-V, nowadays known as IBEX, is now belongs to low risk, while RISC-V, nowadays called CV32. Robert, you know the name better than I do. I can't remember.
E40P.
E40P or something is handled by Open Hardware Group. Yeah. So the PULPissimo has grown over the years. I mean, it's a project that has grown quite organically, which is also the reason why we see some of the issues with the code when we look at it. A lot of things in the architecture were driven by tape outs or quick modifications were necessary. But yeah, we put some effort in recently to do some major refactoring and code cleanup. So just a quick overview on the architecture. Of course, in the middle we have the 32-bit RISC-V core, which connects to a low latency memory bus. All of those blocks that I'm talking about right now, we will have a look at in more detail later on, but just to give an overview how everything fits together. So the low memory bus, sometimes called Tcdm bus for tightly coupled data memory, or logarithmic interconnect due to its internal structure. It's just an arbitration interconnect that provides single cycle, low latency access to the memory banks of the system. On the other side, we have the APB interconnect, which connects the core to several peripherals within the systems. So the core can communicate with peripherals within the system through a memory mapped interface by routing to certain addresses. And those addresses will be routed to the APB interconnect and connect to the various peripherals within the system. So most of the I/O peripherals are connected to the micro DMA, which is just some DMA that allows autonomous access to the memory banks from the I/O peripherals. So UART, SPI, I2C, SDIO, all of them are connected to this micro DMA subsystem. Then another important part of most PULP systems, since PULP follows the heterogeneous approach of having efficient general purpose cores and coupling them with even more energy efficient hardware accelerators, you have those so-called HWPs, which stands for Hardware Processing Engine. And this is just a term that we use for accelerators with a special interface that fits well the PULP SoC structure. I guess the most notable detail about HWPEs is that they all have their own master ports to the memories. So the hardware accelerator is programmed by the core through APB through its configuration interface, where the core tells it the start address where to find data to process and where the results should be written to. But then most accelerators will just independently fetch the data from memory without any core interaction, and the core will just be notified as soon as the operation finished through some event line. Any questions about this? No? Okay, then I guess I will proceed. So if you ever had a look at the PULPissimo top level, you will notice that the module structure or the segmentation of modules looks entirely different than the illustration you just saw right now. We can, I mean, if we, let me try to open the file right now so we can just have a quick look at it. Just a second. Let's see. I guess you should be seeing my screen now, right? So the main entry point of PULPissimo, so the single core microcontroller, is within the root directory of the project in RTL PULPissimo, PULPissimo.sv. By the way, I didn't mention that in the beginning, but we encourage you to follow along when we show things. I mean, it just helps if you have to develop with PULPissimo or PULP SoC yourself. It helps a lot if you are already a bit familiar where you find the files and at which code section certain things are specified. But just to quickly scroll through it, I mean, in PULPissimo, you have a lot of signals in the top level, connections, wiring signals, but basically there is this module, the pad frame, there is the safe domain, and there is the Soc domain. Those three modules we have in the top level. So the reason behind this segmentation in three different modules was basically driven by the fact that it's way simpler to specify the power intent if you want to do a chip tape out and you want to have different voltage levels, or you want to turn down or turn off power gates, some part of the systems. It's way easier to do that if you have them in separate modules. I guess that was the reason why it was segmented that way. So the pad frame module contains I/O pads, actually technology specific, technology agnostic wrappers of the I/O pads. The safe domain contains everything that should always be state powered, or regardless of the power state of the chip. So everything that must not be powered down is in the safe domain. And basically everything else is in the Soc domain. We'll have a look at each of those modules in a minute, but first let's have a look at a couple of important top-level signals of PULPissimo. So again, you should see my screen. Yeah, so if you have a look at the port list of PULPissimo, you see that there's not a lot going on. We have the pad wires for all the pads of PULPissimo. Most of them are just normal I/O pads, which we'll talk about in a minute. but we also have a couple of special signals that are important if you do a tape out using PULPissimo or PULP SoC. We have a reset line. I mean, actually, I can also show it in the slides. So yeah, maybe let's start with the PAD install in. So this is a 32 kilohertz input clock, which acts as the reference clock for the internal FLLs within PULP SoC, or acts as the reference clock for clock managers in case we are synthesizing PULPissimo for an FPGA. Then we have the reset signal, PAD reset, which is an active flow asynchronous reset, which is internally synchronized to the various clock domains. We'll talk about them later. Then the boot select pad affects the behavior according to the program in the boot ROM. So this allows to either boot from external flash memory, hyperflash or SPI flash, or it can be used to tell the MCU that we want to do Jtag booting, and then the core will just wait for the debug module to take over, preload the memory, and start the application. An important detail about that signal is that this pad doesn't have any special logic attached. It's just a regular GPIO, and it's actually the program stored in the boot ROM that decides what value of the boot select causes which behavior. So it's not like you have to change any hardware if you want to have boot select equals 1 cause SPI flash booting. It's just the boot ROM that you have to change, and the boot ROM in turn will read the value of this GPIO or of this pad. I mean, it's a read-only pad, and decide what to do in software. Then, yeah, we have the Jtag debug port, which allows bus access to PULPissimo. It allows to debug the core. Since we nowadays have a RISC-V debug unit inside, we can also use it to do single stepping and have software breakpoints. And yeah, to just the normal GDB debugging stuff on PULPissimo that we're used when developing on a desktop computer. This is mainly important if you use the FPGA port or are actually developing on an actual taped out chip, because in RTL simulation, using the debugging feature actually emulated with the RISC-V debug unit is just way too slow for any reasonable debugging in software simulation. Yeah, then another signal that's not part of the list would probably be the pad test mode enable. So switch again to the code. So actually, did we remove that lately? Oh no, it never was an actual pad. So throughout the code base of PULPissimo, you see this test mode signal or test enable signal, and it is propagated pretty much through all the hierarchy of PULPissimo and PULP SoC. And I mean, the intention of the signal was to have it bypass clock gates, manual clock gates, and cause certain modules to go into a testability mode for DFT, so design for test. So it's not used everywhere. Most modules just add a port but don't make use of it at all. Some modules will actually attach it to clock multiplexers or manual clock gates, which will cause them to always apply a clock if the enable signal is asserted. So we can actually do scan testing. Otherwise, if no clock was applied, scan testing wouldn't be possible. That's the role of that signal. Just if somebody of you were asking yourself what it was used for. Now that we talked a bit about the different signals we have in the top level of PULPissimo, I quickly want to draw awareness to a number of issues with the current state of the PULPissimo code base, just some things that you should be aware of when you develop with PULP SoC. So the first thing I already mentioned a bit when talking about the system Verilog coding style in the very beginning, and that is, yeah, is there a question or is it just a problem of a microphone? Again, if you have questions, please just interrupt. Otherwise, it will be a pretty long monologue of me. So the first thing is parameters. So throughout the code base, you will see a lot of parameters, but as mentioned, a lot of them are not actually supposed to be changed. I mean, this one is defined as a local param, but you also see a lot of modules where you have parameters that seem modifiable. Maybe they even were parametric and it worked changing them in the past, but at some point new modules were added as sub-modules within that particular IP, and changing the parameter no longer works. So if you want to change a parameter, always check whether this is actually supported by all downstream IPs that where the parameter is propagated, and never just assume that it works if you change, for example, the address width, or if you change, I don't know, the number of memory banks or number of private banks. Sometimes stuff is hard-coded, assuming a certain value of the parameter, and then changing it with the parameter is not enough to make it work. The other problem is that there is a lot of dead code, again, because PULPissimo, PULP SoC grew organically, and there are some code places that are no longer used anywhere and don't have any effect whatsoever on the design. The reason probably was that it was used in the past, and then someone had to quickly remove it because he wanted to tape out PULPissimo for a certain chip and didn't remove every trace of a past feature. For example, this CVP address width seems important since it's in the very beginning of PULPissimo and one of the crucial parameters. But actually, if we scan the whole code base of PULPissimo for that particular parameter, we see that it's nowhere used at all. I mean, it's defined here and not used anywhere else. So if you see a parameter or some feature that you think might be important, check whether it's actually still in the use, and make sure it's not that code. I mean, we will try to remove this legacy stuff that's nowhere used anymore, but yeah, again, I mean, the PULP code base is pretty massive, and since it grew organically, it's not that easy to just refactor everything without stuff breaking. In general, if you want to work with PULP SoC, or I guess any RTL or software project in general that you're not familiar with yet, good code grabbing skills or searching skills are essential to figure out how stuff works. So yeah, make use of your favorite grabbing tool to figure out what's going on within the system. Any questions about this so far? Okay. Yeah, well, this I already said. Then let's jump into the first submodule of PULPissimo, which is the pad frame. As I already mentioned, the pad frame contains technology-independent wrappers of the I/O pads that are used for tape outs or for the FPGA. I mean, in the case of FPGA, it's not actual pads, but just the IO buffer cells used, for example, for Xilinx FPGAs. And there are a number of different signals. Maybe before I talk about the signals, let's quickly jump to the code to see what this actually looks like. Okay. So back in we are. I mean, if we have a look at the top level signal, you see, or actually, let's have a look at the instantiation of the technology independent wrappers. So you see that's this pad functional PD, which stands for pull down or pull up. I mean, this generic wrapper just wraps two different kinds of IO cells, one that has internal pull-ups and another one that has internal pull-downs, which are switchable. I mean, there's a signal which is supposed to change whether the pull-up or pull-down is actually enabled. And then we have a number of ports for this technology-dependent wrapper, which we will talk about right now. So first of all, we have the output enable signal, which is an enable signal for the output driver of the pad. So if you want to have a pad act as a driver to drive some external logic external to the chip, you enable or assert the signal. Then of course you have two signals, an input and an output signal for data that should flow from the pads to the SoC. So stuff that enters the chip should go to the SoC. And you have an out signal for logic that is driven by the SoC and should leave the chip through the pad. Then you have the actual in-out signal, which is not connected to any logic. It's directly routed to the top level port of PULPissimo, or it's connected to the landing pads if it's a chip tape out, or in case of FPGA port, connected to the actual pads of the FPGA. The more interesting signal, however, would be this pad configuration I signal. So this is an additional array of config signals. So it's not a single bit like the other ones. It's multiple bits, parametric number of bits actually, which is used to supply the pad with additional control signals. For example, those config signals might be used to change the behavior of the pad in terms, for example, for driving strength. If you want to have a pad have a higher driving strength, you could use some of the bits of these signals to control the driving strength. This, of course, you would do within the technology-dependent wrapper. So again, if you have a look at this signal, maybe we can quickly open it. Yeah, well, actually, let's use the generic one. I mean, with the generic one, there is not a lot going on, just some wiring. But for example, if we open the same thing for the Xilinx port, you see that this instantiates the IO buffer cell of the FPGA. If that was a chip tape out, you would probably have somewhere else another system verilog file that overrides the module with a version that instantiates your IO pad of choice in that particular technology that you want to use. And of course, that particular IO pad that you're going to use will probably have a bunch of additional signals that you want to control, maybe some integrated Schmidt trigger. Again, the pull down, pull up is already mapped with a dedicated signal, but Schmidt trigger, driving strength are very common examples of things that you might want to control, but is very technology dependent. So the actual role of each of those pad config signal is not hard coded except I think for the very first bit. The very first bit is used for the pull enable, pull down, or pull up. But all the other bits, I think by default, it's 5 bits or 6. I'm not entirely sure, but something in that order of magnitude is used in software to control the pads. So those signals are just attached to some configuration register, and you as a software developer are required to program the right value into this register, which corresponds to the setting you want to apply to your particular technology dependent pad. So it's not the code that enforces you to use a particular bit within the pad config signal for a certain role. Okay, any questions about the pad frame or comments? I mean, if I say something wrong, please interrupt me and correct me. No? Okay, then I will proceed with the next of the 3 main modules within the top level, which is the safe domain. So, as I said, the safe domain contains logic that must not be power gated, and stuff that lives in that module is usually referred to in the CPF or UPF specification in a chip tape out backend, where you specify the intent that certain modules or that IP in the safe domain should not be power gated at all, and maybe has a higher voltage than the others, or just a different voltage than the other modules in your system, and that's why it lives in a separate module. So if we open that file right now, so in PULPissimo, it doesn't contain a lot. It contains this pad control module that I will talk about in a second. And it contains some reset synchronizer logic. So if this was actually, if PULPissimo was used for the chip tape out, this is the module where you would place your power management unit, most likely, because I guess the power manager is something that you don't want to power gate itself. And also, if you have some logic that should always be turned on, like example, the wake up circuit is probably best placed into the safe domain, and then you apply appropriate rules in your UPF specification. So in PULPissimo, we actually have, as you just saw, 2 modules only in the safe domain. The reset generator just synchronizes the reset signal, this asynchronous reset, to the reference clock, so the 32 kilohertz reference clock, and the resynchronized reset signal is only used for modules within the safe domain, which are not a lot in PULPissimo as it is, but might be more if you actually added a power management controller or some additional always on IP to the safe domain. The more interesting of the 2 is the pad control module, which basically is just a huge multiplexer for the IO pads. So as you can imagine, the number of pads that you have available for a certain tape outs is almost always not as many as you actually need, which is why you have to multiplex functionalities of your IO facing IPs to those pads. And this is what the pad controller does. It has, for each pad in PULPissimo, it has 1 or more input signals from different IPs like SPI, GPIOs, I2C, whatever, and it multiplexes between those different functionalities. So you can configure the chip to, for example, route the SPI clock signal on one pad, or a couple of cycles later reprogram the pad in software to instead route a particular GPIO to that pad. Maybe an important thing is that each pad has a number of hardwired roles. So it's not like you can route the SPI clock signal, for example, to any pad. The SPI clock signal is connected to one particular pad only, and you can only choose whether you want to use that pad as the SPI clock pad or as a GPIO, or if there is actually a third role of the pad, you can also use that one. So maybe that's easier explained if we actually had to look at the code. The reason why we should have a look at the code is because that's the only source of truth that you should look at if you want to figure out where your IO peripheral, which pad it is actually connected. Because at times that can be quite hard to figure out. And the pad control.sv file, I mean, you always see the file that I'm currently opening down here. If I'm going too fast, just interrupt me. So in this pad control.sv module, you see, for example, the SPIM STIO pad is connected to either the SPI pad. Wait, no, I have to scroll through it, or the GPIO 0. The camera H-sync signal is either the H-sync signal, of course, or GPIO number 10. Okay, so however, the important thing to note is that the pad control module does not actually contain the registers where you program the select value of this multiplexer. It's really just a combinational multiplexer, and the select signal of those pad multiplexers is actually supplied externally through those three signals up here and controlled by a different module within PULP SoC. We'll have a look at that one later. Okay, everything clear about safe domain and pad frame, or are there any open questions about that particular topic? So since it's awfully quiet, just a quick test. Do you still hear me, or have I been talking for an hour without anybody hearing me?
We can hear you.
Perfect. Okay. Alrighty, then I will proceed with the probably most interesting part of PULPissimo, which is PULP SoC. So it wraps the actual heart of the SoC. So Soc domain in PULPissimo, in the RTL PULPissimo directory in the top level wraps PULP SoC, which lives in a different repository, and we'll come to that in a minute. So PULP SoC was designed to be attached or be used not only in the single core PULPissimo system, but is also used in PULP Open, so the multi-core version of PULP. And this is also why it lives in its own repository, and this is also why it contains many signals or IPs which are only used if you actually connect PULP SoC to a cluster. So you will see a lot of code in PULP SoC that doesn't seem to make any sense, that doesn't seem to be used anywhere. It's just dead signals that vanish at the top level of PULP SoC and are not connected. And the reason for that is just because PULPissimo doesn't have a cluster and doesn't make use of those IPs and signals. So yeah, if we have a look at it again, this is PULPissimo, and basically everything you see here is not within the PULPissimo top level, but lives in PULP SoC. The paths are not indicated here. Those we just saw, they actually live in the PULPissimo repository, but everything you see in that nice illustration on GitHub doesn't actually live in PULPissimo, but PULP SoC. If we have a look at a multi-core PULP, I mean, this is not actually PULP open, it's just some regular PULP with a cluster. Here, what you just saw over here, PULP SoC would be that part over here. So we would, in addition to the safe domain, the pad frame, and PULP SoC, those chips most often have a domain called PULP cluster, which instantiates a multi-core cluster, which communicates with PULP SoC through AXI plug. So there's a AXI bus in one direction and another one in the other direction with some additional signals. It's not exactly AXI, it's AXI plus some additional signals for clock domain crossing. Actually, it's pointers in gray code that are exchanged between the two IPs, between the cluster and the PULP SoC, because they live in their own clock domain. Okay, so now let's have a look at the PULP SoC. So the PULP SoC consists of 5 major building blocks. So we have the FC subsystem. Let me quickly open that one in the code. I always open the stuff so you see where you find it and are just a bit familiarized with the code base yourself. So Soc domain is just a wrapper that actually instantiates PULP SoC over here. And if we go to the file lives in IPs PULP SoC, RTL, PULP SoC. As I said, it's a sub-IP of PULPissimo and thus lives within the IPs directory in case you actually checked out the IPs. We will talk about that in the afternoon, late afternoon, about IP management, but yeah, it's not part of the main repository of PULPissimo. So the FC subsystem would live down here. So that's the actual name of the block. And FC stands for Fabric Controller. I mean, the meaning is a bit debatable, or the naming is debatable if we only look at the single core system, because there you only have that one core, but Fabric Controller stands for the core within the PULP SoC. So in a multi-core cluster PULP, this core would be the one that would configure the IOs, that would offload jobs to the cluster, would program the DMA, etc. That's why it's called the Fabric Controller. That's what FC stands for. So besides the actual core, the RISC-V core we see here, it also contains the hardware accelerators, but we'll have a look at that later. For now, let's just go through the illustration again. So besides the Fabric Controller subsystem that contains the core, we have the SoC Peripherals, which contains all the peripherals in the PULP SoC. So SPI, timer, FLL configuration, protocol converters. The FLLs actually live in a different module that I show you. So actually, this is where the FLLs would live. But yeah, so all IOs, all peripherals, timers, interrupt controllers live in Soc Peripherals. This is also where this micro DMA subsystems that I was talking about when I showed you the PULPissimo architectural overview lives. Okay, then we have the L2 Ram Multibank, which is just a wrapper for all of the SRAMs we have within the system. So Yeah, just a wrapper that instantiates the SRAM banks in PULPissimo. And the boot ROM, of course, that's pretty obvious what it does. This is where the core will start fetching instructions right after reset until some actual program is loaded into the main memory, either by the boot ROM that fetches it from an external memory, SPI flash, for example, or hyperflash, or by a debug unit. So before I talk about the debug module within PULPissimo, of course, everything needs to connect it somehow with each other, and that's the role of the Soc Interconnect Wrapper module within PULP SoC. It arbitrates between different masters masters of the systems. We will have a closer look at that later. Yeah. So besides those major building blocks, so those 5 here, there are a couple of additional modules instantiated in PULP SoC that you might have encountered if you tried to develop PULP SoC yourself or just have a look at the code. There are actually two debug modules in PULP SoC. One is, and the newer of the two is a RISC-V debug module, which consists of actually 2 independent modules, which are both instantiated in the top level. So let me quickly go to that application in the code. Dma Jtag. So actually, let's start with the DM top. So DM top is the debug module, a RISC-V debug spec compliant debug module, which connects to the core and allows single stepping, allows breakpoints, and just basic debug functionality of the core, but it also allows access to the system bus. So it connects to the Soc Interconnect Wrapper, but I'll show that to you later again in the schematic overview. And the other module that belongs to the new RISC-V debug module would be this Dma Jtag, which, if I remember correctly, stands for Debug Module Interface. And this is just a protocol-specific interface to the debug module. So the debug module, the DM top that we just had to look at, is protocol agnostic, while Dma Jtag provides Jtag access to the debug module, and they are actually split into 2 different chapters in the RISC-V debug step, and so it seems kind of logical to also split them into 2 different modules over here. So back to the illustration. The other debug module we have in PULPissimo is the legacy PULP tab or PULP debug module. The code, it's actually called, what was it again? PULP tab. Jtag debug. Yeah, this one, Jtag tab. And Jtag lint debug. So these 2 modules are part of the legacy debug module. We still have it in the system for 2 reasons. One is it's a good fallback option if something goes wrong with the new RISC-V debug module, and still have an option to access part of our, still have a mean to access the chip. And another reason is that it is way faster in memory transfers than what the RISC-V debug spec would allow with the RISC-V debug module. So if you're actually simulating the interaction between the test bench and the core when it preloads the memory, and that's what it actually does when you start the simulation, it will preload the memory through Jtag. And if you were to use the RISC-V debug module to do that, your simulation time will just be way longer. But obviously, you should always test both options when you are taping out the chip to make sure the both of them work. But for regular simulation, it's faster to use the legacy debug module. Yeah, so this one is preferred for simulation. Then we have some CDC crossings and resynchronization logic in the top level, which is only used if you attach a cluster to it. So this is where this AXI stuff is going on. And in the code, this looks something like this AXI slice. Yeah. So for example, this stuff here, this is only used when you attach a cluster to it, and it's just one side of a clock domain crossing FIFO. The other side of that FIFO would be in the cluster. And yeah, you have signals, wiring signals that connect to it. Then a pretty crucial part of PULP SoC would be the SoC clock and reset generator module, this one over here. Which wraps all of the FLLs in PULP SoC, and not only in PULP SoC actually, also in I think the PULP cluster. Yeah, the PULP cluster FLL also lives here if there is a PULP cluster, usually. And yeah, it not only wraps the FLLs but also the reset synchronization logic. So each clock domain will have its own reset synchronizer, which synchronizes the asynchronous active low reset to the rising edge of the corresponding clock domain. Speaking about clock domains, we have a couple of them in PULPissimo. So we have the reference clock. I'm not sure whether you should consider that an actual clock domain. Maybe let me. Does that work? No. How can I back like this? So now you should see everything. So the reference clock is just a signal that is directly driven by the pad install-in. So it directly connects to the reference clock of the FLLs, if you have the PLLs in PULPissimo. So pad install-in is ref clock I. Okay, those two are identical in the beginning. However, you also have a slow clock signal. I mean, maybe let's have a look at the code. Over here. So this was the reference clock I was talking about. And the slow clock seems like that one's renamed somewhere. I'd have to check where that one is actually. But the slow clock is actually used by the timers, the timer module within PULP SoC, and it is directly used as an interrupt source. So I don't know whether it's still made use of today, but you can directly trigger an interrupt from the rising or falling edge of the slow clock. And in the ASIC version, the reference clock and the slow clock are identical. So the slow clock is as well 32 kilohertz. However, in the FPGA, we will talk about that on the second day. The reference clock and the slow clock are not identical. So in the FPGA, the reference clock for some FPGA boards is way faster than 32 kilohertz, just because there is no 32 kilohertz crystal on the board. And it is internally divided to a 32 kilohertz clock. again. So slow clock is always 32 kilohertz. In the ASIC version, the reference clock is 32 kilohertz as well. For the FPGAs, depends on the board. Then we have maybe let's start with the SoC clock signal. This is the fastest clock in PULPissimo. Maybe not in every PULP chip, but at least in PULPissimo, that's the clock that drives almost everything. It's generated by an internal FLL, again in the Soc Clock RST gen. So I guess this one, yeah, this one FLL Soc, this is the FLL for the SoC domain. So almost every logic in PULP SoC is clocked by this FLL. It of course uses the reference clock, the 32 kilohertz reference clock for the synchronization. But again, for the FPGA, stuff looks a little bit different. There we do not have an FLL, but we are actually instantiating some IP from Soc Xilinx IP. I think I used a PLL internally, which might use a different clock than 32 kilohertz. So this part is only relevant for RTL simulation and for ASIC development. Of course, if you actually developed your own ASIC using PULPissimo, you would have to replace the behavioral FLL model with something that matches your technology, some different FLL or some entirely different clock generation IP. And so Soc Clock RST Gen is the place to look at if you actually want to see what's going on, who's generating which clock, and where you have to modify stuff if you want to change anything about the clock domains. The second clock domain in PULPissimo that's generated by an FLL is the peripheral clock. So the peripheral clock is the clock that drives the IO-facing peripherals. However, you have to see that, for example, the UART, which is one of the IO-facing peripherals, has two clock inputs. One is the SoC clock, which drives all of the logic in the IP. And the peripheral clock is the clock that drives actual signals. So for example, the baud rate or the signal of the RX and or actually the TX pad of the UART is clocked with the peripheral clock, while the logic, the FIFO, the logic that fetches data from the memory and the configuration register is clocked by the SoC clock. So if you modify the peripheral clock, you also have to modify the clock divider settings of your IPs to still have the same clock frequency. So for example, if you want to have a clock frequency of your I2C of 100 kilohertz, you have to make sure that you also update the configuration register of the clock divider within the I2C peripheral once you update the peripheral clock. If you change the SoC clock, that doesn't affect the clock frequency at which the peripherals toggle their pads. It just changes the speed at which you can interact with the digital logic of the peripherals. There are proper clock domain crossing modules between each of those clock domains I was just talking about, those three. So there are there is handshaking. Most of the time, I think we use clock domain crossing FIFOs to synchronize between the two worlds. And of course, if you actually had a cluster, you would have an additional clock, which is the cluster clock, and you can also see that in the code. So there is a third FLL, the cluster FLL that generates a third clock. And as I mentioned before, the clock domain crossing between the SoC and the cluster happens through those AXI clock domain crossing FIFOs you saw in the top level of PULP SoC. Okay, then let's continue with the Fabric Controller subsystem. I think I'll skip showing you the code about this, but yeah, I mean, this is just another submodule of PULP SoC. And as I said before, it instantiates the RISC-V core, either IBEX or risky. It's actually still risky. So the core that's instantiated is a version of CV32E4DP. Before it was donated to the Open Hardware Group, so it's still referencing the old risky IP, not the updated one by Open Hardware Group as of yet, but that will probably change in the not so far future. Then we have hardware accelerators. In PULPissimo by default, there is a multiply accumulate engine, the Mac engine, but this would be the place where you plug in your own hardware processing engine if you want to have any in PULPissimo. And yeah, I guess the reason why they are placed together in the same submodule, although they do not directly interact with each other, was for simplifying power intent specification. But yeah, hardware accelerator and RISC-V core do not interact directly with each other at all. So both have their own ports, and they communicate with each other through the SoC interconnect and through the interrupt or through the event handler in the peripherals module that we'll see in a minute. What you also have in the FC subsystem, Fabric Controller subsystem, is an interrupt controller, which, yeah, I mean, there's nothing special. It just has 32 interrupt lines, right? All that, 32 of them. And yeah, it connects to a number of more interrupts, like maybe it's easier to show that in the SoC peripheral. So the SoC peripheral would be another submodule of the PULP SoC. You see that over here. This one over here is the one I'm talking about right now. It's as well in the IP's PULP SoC, RTL PULP SoC directory. And this is where all the peripherals live, as I mentioned before. So there is a timer module which connects to the slow clock. And there is the hardware event controller, which I wanted to make a reference just now. So Risky has only 32 interrupt lines, or actually the interrupt controller of Risky has 32 interrupt lines, while there are many more interrupts or events in the whole SoC. So almost every peripheral exposes some sort of interrupt, or as we call it, or source code calls it, event. And the hardware event controller is basically just an interrupt extender. So it accepts several interrupts from the peripherals, also from the hardware processing engine, and maps it to a single one of 32 interrupt lines of Risky. So Risky will be interrupted with one interrupt line, and then software has to communicate with the hardware event controller, so the Soc event generator, to figure out which event actually triggered the interrupt.
So can I ask a question here?
Sure.
Do you mean the event unit is the same thing with the interrupt controller?
Sorry, can you repeat that?
If you go to the diagram you show previously, there's interrupt controller, right? And I think in PULPissimo's diagram, that the very generic one, at the beginning of the training you show us, there's a event unit. I'm just wondering if this means the same thing. This one, there's a interrupt controller at bottom, right?
Yes.
Yes.
And on the right hand side, there's if something after events go to event unit, right? Is these two terms mean the same unit?
And also there is an interrupt controller with 32 lines, but there is also the event unit, which is basically an interrupt multiplexer. So it multiplexes a lot of more interrupts than 32 onto one interrupt into this interrupt controller. So those event unit and interrupt controller are two separate things. So in some sense, the interrupt controller is like the CLIN, and the event unit is more like the click. But it's I mean,
yeah. So I guess your question was whether this event signal here actually relates to interrupt. And yes,
yeah.
The naming of some of the signals in PULP SoC is a bit unfortunate. So the event signal you see here should actually be called interrupt, because those are the 32 interrupt lines I was actually talking about. So the interrupt controller receives those 32 interrupts, which are unfortunately called events. And those 32 interrupts are actually assigned in the Soc Peripherals over here. So events, FC events. Oh, it should be this one. Yeah, there it is. So for example, you can see interrupt line number 15 is used for GPIO events, whatever that's going to trigger. I guess some rise or fall event. Then you have some timer events. Then you have what I mentioned before, rise or fall event of the slow clock. And you should have somewhere, do you spot it, Robert? Where's the event?
Which one?
Units, the one from
yeah,
the
this
event.
is this 26. You see the big comment block there? So you mean this, right?
No, but this one is not actually connected. Is it the event?
No, but this is the one which is reserved for the event unit interrupt.
I guess it's those ones, right?
No, this is for the HUP.
No, it is this one. So this is the Soc event generator. This is this extender of interrupts I mentioned before, right? So this one. And in the code, it connects to the interrupt line number 30 and 31. And then there's an additional signal for errors in the event controller.
Okay, thank you.
Any additions from your side?
I mean, my point is that you see there is not connected, but it's reserved. So this is where the interrupt events are being maxed to this interrupt. It's just connected at another place.
Mm-hmm.
So the three events below, they are actually, I don't recall, but they are not from the event unit in that sense.
Mm-hmm. Okay. Then back to the overview of the Soc Peripherals. So of course you also have a Gpio controller, which just provides basic Gpio functionality. So here you can read Gpio's value, you can set a value. I think you can configure interrupts to trigger for a rise or fall event. But this is not the module that's responsible to decide whether a particular pad actually acts as a Gpio or is controlled by some of the peripherals like SPI or I2C that would be controlled in this part here, which I will talk about in a second. So actually all of the IO facing peripherals, I2C, SPI, I2S camera is wrapped in over here in the micro-DMA subsystem. This micro-DMA subsystem again has a configuration port. So what you saw in the very beginning about the PULPissimo architecture, we had this APB bus, which allows to communicate with the configuration interface of the peripherals. And this is where this one plugs in. It goes into this peripheral bus wrap module, which just demultiplexes transactions, right, to the different peripherals. And one of them would be this micro-DMA subsystem, which in turn has its own master ports to the Soc Interconnect, so the DMA can independently fetch data from the memory or write data to the memory. For example, you could configure your SPI to independently fetch data from an external sensor and write it to memory starting from a particular address, and the micro-DMA would take care of it through the T-export to send the data to the main memory. Now, the last very important IP in Soc Peripheral is the APB Soc control. So this is a fancy name for something that's not more than just an APB, a register file with an APB interface. So the register file stores configuration which is global to the whole SoC, and probably, I mean, this table gives a summary about the most important register in APB Soc control. You have the boot address, which controls where the core starts to fetch data. You have a fetch enable bit or fetch enable register, which controls whether the core is fetching instructions and actually doing anything useful. And it is by default controlled with an external signal, and the default is 1. So after reset, the core will always immediately start fetching instructions from the boot ROM, which is the default start address or default boot address. Then we have the Padmax Register. So this is the place where you would tell the pad control module how you want to multiplex your pads, how you want to use each of the pads. So there are, for most pads, there are 2, sometimes 3 different values. So 0, 1, or 2 that you can write into each of those registers. There is one register, or actually I think they are fused to single registers. There is a field in the register file for every pad where you can configure the role of the pad. And I think the default for most pads would be to be connected to the specific peripheral. So the example by default, the simple level. So for example, the pad UART TX pad by default is connected to the UART IP. if you don't change anything. If you actually wrote something else into the APP Soc control IP, yeah, there they are, pad function. There are 4 of those registers, and they just control the different pads of the system. If you wrote something else than the default value to those registers, you could actually connect the pad to the Gpio peripheral and have it act as the Gpio. Sometimes there is even a third pad function mapped to a single pad. Then, yeah, you would have to look up in the pad controller what each of the function values would cause the Padmultiplexer to do. Then pad configuration. This also goes back to what I talked in the very beginning. This is the register that contains those technology-dependent pad configuration signals. Here you could write a particular value for each pad, and that value would be propagated to this pad config signal in the pad frame. So if you wanted to change the driving strength of a particular pad, this is the register that you have to address, and this is where you have to change the configuration. Of course, this assumes that you are actually using pads that have a driving strength configuration signal. But yeah, again, the role of each of the pad config bit is not fixed and depends on the pads that you're actually using in your paper. Then the final one is the Jtag register, or the core status register. Yeah, so the Jtag register is just used for some interaction between the general purpose core, or let me phrase it like this. The Jtag register is a register that doesn't have a fixed meaning. It is just used for general purpose stuff when you interact with the Jtag. So the Jtag interface can write to it, and the core can read from it, and vice versa, if I remember correctly. And it depends on the software or the software environment that you're using, whether that Jtag register is used for something special. However, the more important kind of general purpose register is the core status register. Again, this is just a 32-bit register. It doesn't connect to any special IP or hardware, but it has a special role for all of our PULP software environments. So PULP SDK and PULP runtime. Robert will talk about those later. But the core status register is the register that's the runtime. So the software, once it terminates the main function, it will jump to a place in the runtime that will write a particular value to the core status register. And this will be the exit code of your main function and an additional bit. And this doesn't really matter, but the important thing is the core status register will contain the exit code of main, the return value of your main function. And this is the register that's used by the simulation environment, by the test bench, to check whether your software terminated execution. So the test bench will constantly poll this register after it enabled the core until it reads an expected value. And the expected value would be the expected return value of main. And once it sees that value in this register, it knows, okay, my main function terminated execution. I can terminate the simulation in the test bench. Any questions about this? So I guess this would actually be a good place to quickly show you the PULPissimo documentation page. Let me quickly go to GitHub, because we actually, Robert put some effort into updating the PULPissimo datasheet, which contains the memory address mapping to all of the IPs and the role of all those registers in the APB SoC control. So if you go to PULPissimo documentation and then to datasheet, let's open that one. There we are. You will see that we have a memory map where you see where each of the peripherals is mapped to. So again, all of the IO facing peripherals, you have to look for them in the micro-DMA, underneath the micro-DMA. But for example, the Soc control, you see the start address would be at 0x1A104000. And if we go to the APB Soc control over here, you see what each of the registers I was just talking about is used for, probably in more detail than I just mentioned it. You see what each of the bits is used for. So if you actually want to directly interact with the hardware without using some of the drivers that we supply, this is the place to look at what it's actually used. I mean, you correct me if I'm wrong, but the documentation is not automatically updated from the source code, from the RTL source code.
Mm-hmm.
This is something that we really would like to have. So having a single source of truth for both the RTL source code as well as documentation and drivers, but at the moment that's not the case. So it might be that at some point the datasheet and the source code goes out of sync. And then, of course, you would have to check the RTL to figure out what really is used as the address. We will try to mitigate this issue to some degree in the future by using a tool that Robert will introduce to you in the afternoon. But for now, that's the way it is. And you always have to take information from the datasheet with a grain of salt, or just being a little bit, having a healthy amount of skepticism about the information you see in the datasheet. Okay. Then again about the L2 RAM. So the last part, I mean, if we quickly go back to the overview of PULP SoC, we have the L2 Ram Multibank. Again, this is the wrapper for all of our SRAMs within the system. We will talk about which banks we actually have in the system in a second, but for now it's suffice to say that within this SRAM wrapper, or in this wrapper of SRAM banks, this is the place where address conversion happens, because the SRAMs up to the interface of this multibank module, we still operate with 32-bit addresses, which are byte addressed, while of course for the SRAMs themselves, they have less than 32-bit address lines, and furthermore, some of the address spaces that are mapped to a particular memory bank do not start at a natural boundary. So you would have to subtract a certain offset from the address in order to apply to the actual SRAM and have it start with 0 instead of some weird offset. Furthermore, the SRAM banks, all SRAM banks in vanilla PULPissimo use 32-bit word addressing, not 8-bit addressing, which is also why we have to cut off the 2 least significant bits of the address before we apply it to the SRAMs. So misaligned load and store accesses are taken care of in hardware by the RISC core. and whatever arrives to the SRAM banks is supposed to be already aligned to the natural 32-bit word boundary. In addition to that, it contains the protocol conversion. We'll see that later when I talk about the Tcdm protocol, but this is the place where the handshaking for the SRAM is taken care of, because the SRAMs do not use a special handshaking protocol. You just apply an address, you enable the SRAM bank, and you will have your result if it's a read access one cycle later, most of the time. Depends, of course, on the particular SRAM you're using. Okay, any questions about the memory banks? No? Okay, then I guess the last part about PULP SoC before I start my monologue about the architecture of PULPissimo and PULP SoC is the SoC interconnect, which is a pretty crucial part of the whole system. Some of you that might had a look at earlier versions, and by earlier I mean older than 4 days, 5 days of PULPissimo master, we're still had a look at the old interconnect that was completely rewritten a couple of weeks ago and was merged a couple of days ago into the master branch of PULPissimo. It's not yet used in the cluster version of PULP. We have to check some metrics of the new interconnect first and performance before that's merged there as well, and see whether there are no regressions in area and timing. But at least in PULPissimo, it's already part of the master and the latest release of it. So maybe let me quickly go to the file itself. We go back. So within PULP SoC, we have this SoC Interconnect Wrapper. This is where the interconnect is instantiated, and this is where most, if not all, of the other components in PULP SoC connect to in order to communicate with each other. As you can see over here in the port list, it has a bunch of master ports. I mean, of course, they are slave from the perspective within the interconnect, but these are the master ports that can load and fetch data from the memory. You have the fabric controller data port. Of course, this is the data port of the RISC-V core. Obviously, the RISC-V core also has an instruction port. And you have 2 ports for the micro DMA. You have a TX channel and an RX channel. So the micro DMA will write data to the memory through its TX channel, and it will receive data or read data from the memory through the RX channel. The fifth port would be the Tcdm debug port. This would be, maybe let's go back here. PULP SoC overview over here. This would be this port over here. It comes from both of the modules, the legacy one and the new RISC-V debug module. And what I did mention before, they only have one access port, one master port to the interconnect, and they go through some arbiter. It's just a demultiplexer that arbitrates between the access of the legacy module and the new module. So this will be this port. So here. Then we have the master ports from the hardware processing engines. It's configurable how many of them you have. I think the Mac engine uses 4, but I might be wrong here. And you have the master plug from the cluster, which is unused in PULPissimo. So this is the AXI interface where the cluster can fetch data from the shared L2 memory. So there it would fetch its instructions and data with a DMA. And this is a 64-bit AXI, and this is a 32-bit AXI. So the connection into the other, for the other way. So if the SoC wants to communicate with the cluster, this happens through a 32-bit AXI block. So if the fabric controller, the risky core, wants to enable the cluster or wants to communicate with the cores of the cluster, this would be the plug where the communication happens. Yeah, so this was already one of the output ports of the interconnect. Another output port is, of course, the APB bus, which connects to the peripheral subsystem and connects to all the configuration interfaces. And obviously, you have a number of ports for slaves, for the memory slaves. And maybe it's easier to explain that if you have a look again at the illustration of the SoC interconnect. So the interconnect basically demultiplexes transactions from the masters. So the fabric controller, micro DMA, debug port, and the transactions from the cluster, which are converted to the Tcdm protocol. We'll see that just in a second. So the transactions from these masters are demultiplexed into 3 different domains. The first domain would be the interleaved region, which connects to the bulk of the memory within PULPissimo or PULP SoC. This is logarithmic interconnect that provides single cycle latency access to the memory banks, which are word interleaved, whose words are interleavingly mapped to the different memory banks. So sequential word addresses in your address space are mapped to different memory banks. So for example, an address with the last bits being 0, 0, always 0, would be in memory bank 0, and the next 32-bit address would end up in memory bank 1, and so forth. The reason we have this interleaved address space is that if you access an array from multiple masters, for example, from a hardware accelerator, you end up with less memory bank conflicts as if you use this sequential address space where sequential addresses are all mapped to the memory bank, to the first memory bank, and the next subspace is mapped to the second memory bank, and so forth. So if you have this interleaved mapping, it just reduces the number of bank conflicts. Then the second region where transactions might end up, this is of course depends on the address. So the Tcdm demultiplexer decodes the address of the transaction, and depending on the address prefix, it will route them to one of 2 regions. And the second region would be what I call the contiguous region, where address space is sequentially mapped to output ports. And in PULPissimo or PULP SoC, we have 3 of them. We have the private bank 0, private bank 1, and we have the bootron. So it's not like those banks are actually private. They only differ from the memory bank in the sense from the interleaved memory banks in the L2 memory. So actually some software calls this the L2 memory, and in some illustration you see this part over here denoted as the L2 region. However, Private banks are just some other SRAM banks that do not have interleaved address mapping, but all of the address space is mapped contiguously to a single bank. And they are there mainly in order to improve performance for the core. So most linker scripts used in our software environments will place the instructions of the core in private bank 1, if I remember correctly, and the stack preferentially in private bank 0, which of course has the effect that if you place the bulk of your data that your hardware accelerators use, that your micro DMA is accessing, this will have the effect that the banks which will contain the instructions and the stack will never have a bank conflict because the core, the fabric controller, is the only one accessing them. But this is just a linker script placing them there. It's not like this is enforced by hardware. And also if your application doesn't fit into the private bank, the linker script will just fill it up in the interleaved region if necessary, which of course will degrade performance because you will share access to the individual memory banks with all other masters in your system. But yeah, that's the way it is. Bootrom, of course, this is read-only access. Yeah. Then, so both regions I was talking about so far, so those with the blue shading in the illustration use a protocol that we call the Tcdm protocol. Tcdm for tightly coupled data memory. So the Tcm protocol is a single cycle latency protocol, so you can within a single cycle read and write to the memory, and it supports, I mean, since it's single cycle latency, it inherently supports burst. You just have a transaction in every cycle and you automatically have burst. So it is used for communication between the core and the memories, but it's also used by the hardware accelerator and the micro DMA as well as the debug port. So basically everything that can access the memory is using the Tcdm protocol. Important to know is that the Tcdm protocol, although the signals that we will have a look at in a second might seem like it doesn't allow multiple outstanding transactions. I mean, the problem with the Tcdm protocol is that it's not specified very well, and it's a bit hard to wrap your mind around how you have to use it to be compatible with all the IPs in PULP. So I'll talk about that later, but yeah, the Tcm protocol is very good if you need single cycle latency to the memory, fast access to the memory, but probably not the best choice if you want to have access to peripherals which have dynamic delays or variable delays. So I guess the key rule about the Tcdm protocol that you always need to make sure that your IP, which exposes a Tcdm interface, is in compliance with, is that the request line, maybe let's have a look at the signals here. So you have the request line, which is the line that the master of the protocol asserts in order to start the transaction. So the request line must not combinationally depend on the grant line. I mean, it's similar to OXI in that sense. So the valid line must not depend on the ready line, if I remember that correctly. But in order to start a transaction with the Tcm protocol, you just assert the request line from the master side, while simultaneously applying the address to which you want to write or from which you want to read. Of course, you also apply the write enable signal. However, take heed that this WEN doesn't stand for write enable, it stands for write enable negated. So this is a negative low signal. If you want to write, you pull the signal to 0 or logic low. If you want to read, it should stay high. Byte enable signal, some IPs can make use of it to only write specific bytes, but it's not all IPs support. For example, the SRAMs, obviously, the SRAM macros we use in PULPissimo don't support this. Yeah, that's it for the signal from the master to the slave. On the response side, you have the grant signal, which is the signal that the slave asserts if it wants to accept a transaction. So in the cycle where both request and grant signal are asserted, this is when transaction is considered valid, and this is where transaction takes place. The grant signal might be delayed, so it can be that the master asserts the request line and the slave waits for a couple of cycles before it asserts the grant signal. But since it's a single cycle latency protocol, it's actually legal for the slave to combinationally assert the grant signal on request. So in the same cycle that the master asserts the request, the slave is allowed to assert the grant. This is how you arrive to single cycle latency and with a throughput of 1 transaction per cycle. However, there is also an additional signal, which is this R-valid signal down here. This is the response valid signal. And yeah, this is a bit of a point that's debatable how useful that signal is or not, because the problem with the signal is that not all IPs in PULP actually support delaying this signal. So of course you can delay the assertion of the grant signal if you want to apply back pressure to the master, but there are some IPs that do not support delaying of the R-valid signal by more than 1 cycle, or not more than 1 cycle, but they only support it if R-valid is asserted exactly 1 cycle after you asserted the grant signal, like this. So the master wanted to start a transaction in the 2nd cycle. The slave didn't accept the transaction yet. It delayed by it stalled by 1 cycle. In the 3rd cycle, it accepted the transaction, and 1 cycle later, it's delivered the read data to the R data signal. This, on the other hand, would be an example where the slave immediately accepts the request. You have the master asserting request, and you have the slave asserting the grant signal combinationally in the same cycle. And exactly 1 cycle later, R-valid is asserted, and you receive the read response. And you can have those transactions back to back. So 1 transaction per cycle. Yeah, so one thing to be extremely cautious about configure or working with Tcdm protocol is that it's extremely easy to introduce combinational loops between master and slave if you're not careful with what you're doing. Reason of that is, of course, because you have a combinational path between request and grant, because the protocol allows this. Yeah, you have to be a bit careful on not to introduce such a combinational loop, especially when you write a master. So if you write a Tcdm slave device, one that just accepts transaction, then it's less of a problem because the protocol actually allows the grant signal to combinationally depend on the request, but the other way around is more critical. So if you write a hardware accelerator that by itself can access the memory and issue requests, it's very easy to involuntarily have the request line through some weird FSM state combinationally depend on R valid or on grant. And this will cause a combinational loop in your system, and it just doesn't work if you try to synthesize it that way. Any questions on the Tcdm protocol?
Yeah, I have a question. I didn't understand what triggers the grant signal down in the second case, and also what happens to the R data in the second case as well. Like why there is like yellow, empty, and then blue.
Which second case do you mean? Which...
When in the second case, I mean when grant triggers on the same cycle as request.
Over here, you mean?
Right? Yeah, so the second set of requests.
Okay, so in this particular cycle, you see that the master started a transaction, right? Which is relating to this yellow address over here, and the slave immediately granted the transaction. This would be the normal case if you access an SRAM bank and there is no bank conflict. If there is a bank conflict, one of the two masters might be delayed, exactly like this, right? One of the masters would see this kind of transaction and the other master would have its transaction accepted in the same cycle. And one cycle later, you receive the response of the data. And then you see in that particular cycle, again, the master was stalled. This is why you don't have any legal output in this cycle over here. Again, the slave stalled the master for one cycle and again accepted it one cycle delayed. If you imagine this particular case here, I mean, ignore that the first transaction was delayed by one cycle, but if you have a look at this, here you see a case where master and slave have transactions in every cycle back to back. So in the same cycle as the request line is asserted, the grant line is simultaneously asserted, which marks a valid transaction. Does that somehow explain or resolve the question, or?
Yeah, I think it clarifies a little bit. Yeah, thank you very much.
Okay. Any other question about the Tcdm protocol or about the interconnect in general? No? Okay. Then I will talk about the last part of the interconnect, which is the AXI crossbar. That's something pretty new that was not present in the old interconnect. So as I mentioned before, the Tcdm protocol might not be the best choice to use for interaction with peripherals with variable delays, especially if it is not possible to delay the grant signal. If you, for example, pipeline or try to pipeline your interconnect, then it's no longer possible, or it's not as easy anymore to decide within a single cycle whether a slave can accept the transaction or not. And for this particular case, AXI is just a better way. Also, I mean, AXI is standardized and compatible with IPs outside the realm of PULP. So maybe let me, and I will show that later in the code, but the AXI crossbar in vanilla PULPissimo only has two output ports. I mean, of course, it has many master ports, one for every master in the system, but there are only two output ports right now. One connects to the cluster. This is the 32-bit AXI plug I mentioned a couple of times before that connects to the PULP cluster if there is one. In PULPissimo, there is not. And the other output port would be the plug that connects to the SoC peripheral. Of course, it first passes through a protocol converter, which converts from AXI4 to APB, because the peripherals use APB. But those are the two output ports that you normally have in PULP SoC. However, as you can see in this illustration, the Soc Interconnect is basically wrapped, or consists of two modules. You have a wrapper around it, which is of course the one that's instantiated in PULP SoC, and you have a parametric core. And maybe it's easier if I just show it in the code right now, how that one looks. So this would be the Soc Interconnect Wrap file, again in the PULP SoC IP. And it, of course, instantiates all the wiring signal that you need. We saw those before. We have the ports of the signal, ports of the interconnect, the specific ones. But inside this wrapper, there is a parametric interconnect which doesn't care about core instruction fetch port or AXI port or whatever. It just has a number of master ports. All of them are Tcdm masters. It has a number of slave ports. So that would be the number of interleaved slaves. It has a number of contiguously mapped slaves. As I mentioned before, the two private banks and the boot drum. And it has a configurable number of AXI slave ports. So it is very easy to adapt the interconnect to have different numbers of output ports. If you want to attach a new AXI slave, which is what we're actually going to do tomorrow, you would just reparameterize the module within the wrapper. And it's the wrapper that takes care of attaching the right port to the right, interface to the right port of the parametric Soc interconnect, this guy here. What the wrapper also does is it specifies the address rules. So this is this part over here. What I didn't mention so far is how those individual crossbars and demultiplexers actually decide where a transaction has to end up. This is what the Tcdm wrapper, in conjunction with another file, the Soc memmap. So if you go to PULPissimo, RTL includes, there is one particular file called SoC memmap for memory map. And this is just a header file which contains a number of defines for the different start and end addresses in the system. I mean, those are just defines. They don't do anything by themselves, but it's just a neat way to have them defined at a single place in a header file. The reason why it's in a header file and not in a package, and why it's not within the SoC, is because the cluster variant PULP Open might use a different memory map than PULPissimo, which is why that information is supplied externally. And yeah, this is also the way it was handled to some degree before writing the new interconnect. However, I mean, here you can, maybe it is easier if I do it like this. So here you have address rules. I mean, it's probably a bit hard if you are not familiar with the address decoder IP we have in the common cells. We'll talk about that when we introduce the different IPs we have for developing PULP, developing with PULP. But what these lines basically read as is, you have start address, you have an end address. For example, this is for the let's have a look at the AXI crossbar. So in the AXI crossbar, we have by default 2 output ports, right? Port 0 and port 1. And these are address rules that which tell the AXI crossbar which address regions should end up at port 0 and which ones should end up at port 1. So for example, everything with the AXI clock start address, it would be this address here, between this start address and this end address, should be routed to port 0. Everything between the peripheral start address and end address should be mapped to port 1. You can have multiple memory regions mapped to the same port. That's perfectly legal, and which allows you to have a segmented memory space for your output ports. The same kind of rules you have for the other crossbars. So you have a set of rules for the demultiplexer up here. It would be these rules here, over here. The L2 demultiplexer rules. This reads as follows. You have the private memory bank start address and the end address mapped to port 1, which would be this port. So this is port 1, this is port 0, port 1, port 2. You would actually see it in the code, but I'm telling you right now. So the contiguous region is mapped to port 1. You have the Tcdm start address mapped to port 2. And you probably noticed that there is no rule which should be mapped to port 0. So port 0, to remind you, port 0 maps to the AXI crossbar. So this is port 0. Everything that doesn't match, every address that doesn't match any of the rules defined in this structure here automatically ends up in the AXI crossbar. That's just the way it's implemented. So there is no dedicated region for the AXI crossbar. Everything that's not specifically mapped to either the interleaved address space or the sequential address space for the private banks and the boot ROM is automatically an AXI address, and where exactly that transaction is routed to is defined in the AXI rule set down here. This might be a little bit abstract right now. You will get more familiar with that when we do the exercise where you're actually integrating a new IP into PULP SoC. Okay, so after this rather long monologue before we have, I guess, a lunch break, are there any open questions about the SoC architecture in general, about PULP SoC, about PULPissimo, or everything that concerns the architectural structure of the SoC? No questions? Okay. So I guess, right now I talked for almost 2 hours. So I guess we have break until 1 o'clock. Does that sound reasonable, Robert, for you as well? Yeah, so in the afternoon, we will continue. This was a rather, kind of boring introduction on the SoC architecture, but it will be important once we do the exercises where you have to modify parts of the ASIC or of the SoC. In the afternoon, Robert will take over and will introduce you to the software environment. And there will be also some parts, as we mentioned in the introduction round, about IP management and hands-on exercises on both the software environment, software simulation, and for IP integration.
So on the afternoon, there will be some software exercises, very simple ones, just to get you started, to check if your setup works, and to see if you can do some simple integration stuff into the software environment. And all these things will then be used in the second day, or are more elaborate
Yeah,
sequence of
I guess, I mean, the exercises will become more involved as we progress, and I hope also more interesting as soon as we made you familiar with some of the skills necessary to modify PULPissimo. Okay, so if there are no more questions right now, I'd say we continue at 1 o'clock in the afternoon. And I will stop the recording right now, and yeah, we'll see each other again at 1 o'clock. Anything you want to add, Robert?
No, fine. 1 o'clock is in 1 hour and 30 minutes. 13 minutes.
Yes, exactly. Okay. Then see you all later.
Not do much more than just a boot PULPissimo to main. So it will set up the stack for you. It will initialize a few hardware specific things like the FLL, the interrupt mechanisms, and so on. And then you are in main and you are on your own. There's a small UART driver to help you like do to help you debug on FPGA or on real hardware, but there's not much more. So this PULP runtime is really meant for people that want to build on top of it, and for people that like to poke the hardware they write with, like poke the registers, or just write minimal proof of concepts, or write minimal drivers for their hardware. So it's really meant to be something very low level and something that you can understand in a short time without having to deal with a lot of with a complicated setup or a big tool chain and so on. And it's very actively developed. Okay. So PULP runtime, I talked a bit already about it. So really the main point is boots from the boot ROM to over the CRT0 to main, you have a C runtime. That's it. There's only a UART driver, and there is a HAL, available hardware abstraction layer, which helps you like bit bang the registers of the existing hardware. Okay, so now let me show you like the specifics of the PULP runtime. So the PULP runtime has so this is the folder layout of the PULP runtime, and most importantly is the kernel. So the kernel, it says kernel, but actually there's not much of a kernel. All it does is initialize the FLL, set up the stack, and then bring you to main. There's lib, the lib folder. In the lib folder, we have some small C library function, but it's not a full libc. It's mostly just printf and a few exit and a few other functions. We have a drivers folder, which doesn't have much more than the UART. We have a few scripts that help you debugging. We have a configuration folder, so that before you use the PULP RAM, you have to tell it what kind of chip, what kind of hardware you are targeting. And we have a bin folder where we have a few more scripts and binaries that help you deal with FPGA setups and so on. So let me maybe dive into these folders. Sorry. Okay. So I'm now in my PULP runtime folder, and this is these are the directories I promised. So let's go into the bin folder. As you can see, in the bin folder, there are a few GDB. There's a GDB script. There is some scripts for dealing with the Genesis 2 FPGA board. Most importantly, there is the StimUtils Python script. So how it works is that this Stimultils Python script is being used to convert an ELF file into something that can be loaded on into the FPGA, or something that can be loaded into the vSim test bench in the RTL test bench of PULPissimo. So really, this script is being invoked to do this conversion process. We will see maybe later how this exactly ties into when you launch a simulation. Okay. Next, we have the configuration folder, which I've mentioned before. So this configuration folder is a set of script that you're supposed to source into your shell, and this will set for you a few environment variables so that when you launch, so that when you use the make files of your application, it will know where the PULP runtime is and what kind of platform you're targeting. For example, when we look into the PULPissimo sourceable script, it does not do much more than set 2 variables for you, and that's it. And the other magic down here is just to make sure that you can source this script from any location. Okay. Let me show you maybe this. Yeah, so this is just the other script that is always being sourced. Okay, so this is the configuration folder. Next, we have the driver folder. So in drivers, as it says there, you're supposed to place drivers, and we don't have much more than a UART driver in the PULP runtime. As I said, the PULP SDK, which is currently also being overhauled, there are more drivers, there is more to do, but as I said, the goal of the PULP runtime is to have something very minimal, something that gets you going immediately. Okay, the next we have the kernel. So it's called the kernel because this is because it was a part, so it's historical name. But anyway, what the kernel mainly does, you can see it here. There's a file called FLL and there's a file called IRQ. So it configures the FLL to generate the sensible clock, and it configures the interrupt controller to disable all interrupts. And it sets up the stack for you. So we can see this in the CRT0S. So it sets up for you a C runtime, and then you basically immediately go to main. Okay, this can't be seen here because there is some more initialization code that is being run. But anyway, afterwards you will be in main. Okay, we will. Let me see. Next we have lib. So as I promised, it's called libc, but it's not a full libc. So what it supports is mostly printf. So this is just for debugging, and it's obviously it's meant to be super small so that it doesn't bloat your code. And then finally we have we have the rules folder. This is a set of make files that is being used to compile the program. We will look into this next. And there is a scripts folder with a few helper scripts. So one helper script we have is the bvrun-test Python script. Normally you don't use this, but this is meant to run a set of tests and in like your CI pipeline or something, and it generates for you a JUnit XML files, which you can then tell GitLab about, and it can render for you like the test results, how many things passed, how many things failed, and so on. And then we have the pub-trace script. I will demonstrate this later too. The pub-trace script is basically a helper script. It helps you to symbolize your execution trace. So whenever you run a vSim simulation of your program, of some program, for example, Hello World, you can you get a log file which lists all the instructions that have been executed. But these instructions, this is in plain assembly, and in the addresses are all hexadecimal values. And obviously, you can then look at the hexadecimal values and compare them with your binary. So by using object dump or something, or you can just use pulp trace and run this script over your trace. I will produce for you a trace that then tries to symbolize, that means map the hexadecimal values to symbols in the binary, so it's much more readable. So this is a debugging aid. Okay. Let me see. So this is the brief overview of the internals of the PULP runtime. So this was the overview of the internals of the PULP runtime. Now let's look next at the build flow. So here I have listed the build flow, and you can see it is a set of makefile fragments that are being included with each other. And in the end, your application is supposed to include the final makefile, the PULP RT makefile, into your application's makefile, and this will define for you all the targets you will need to compile and run your application. So let me give you an example. So I have here an Hello World application. When you open the makefile of the Hello World application, you will see, let me show. You will see that we set a few environment variables, and then we include this PULP RT make, which I have shown just before. So now let's look at the PULP RT make, what it does. So let me go into PULP runtime, PULP RT make. We open it, it's in the rules folder. So with the makefile fragment, you see it does something very weird. It just includes another file. Now, the reason being is that it is for a compatibility reason with the PULP SDK. The PULP SDK has a certain way of including make files with each other, and we have to kind of declare this dummy file so that we don't have to edit each make file of each application. So this is kind of like a backwards compatibility thing. Okay, next you can see we include this make file here from PULP RT home. PULP RT home just points to the PULP runtime, and PULP RT target is being set by the script you should have stored. So let me show it to you. So just before I showed you that there are in the configs folder down here in PULP runtime, there are the scripts you can source. When you now source, for example, PULPissimo shell, you will see it will export, set these bash variables for you. One of those is the PULP RT target. And this is being used here. So depending on the variable of this, a different makefile is being included. And this is basically how the PULP runtime knows which platform you target, because at this point here, depending on your platform, it will include a different file. Okay, let's assume, for example, we set PULPissimo, we source PULPissimo shell. Let me do this. So I'm going to PULP runtime. I source configuration PULPissimo shell. Then I can just look at my environment. I do an environment. I grab target. And I see, okay, PULP RT target and PULP run target is set to PULPissimo. And you can see when I now would use the makefile in the hello world, go to the makefile, and you would see that it would include now this PULPissimo.make, because that's what the variable has said. Okay, back to the PULP runtime. Let me show you the PULPissimo.make. So now this is like where now it gets more interesting. There are a few things you can see here. So at the top we have the C flags, so the C compiler flags, the linker flags, and a few more environment variables being set. Now you can see that when you want to, when you want to use a different march flag, so when you want to target a different subset of instructions, then you have to edit this C flags here or edit this file. Okay. And in the end, we see more of these nested includes. We see the default.make, which is basically it sets a few default variables. This is not much very interesting. So you can see it sets just a few environment variables. And finally, default rules.make. Now in the default rules.make, we see all the targets we need to compile and to launch the simulation. So let me open this file. Okay, so when we scroll down here a bit, you will see here, these are the default rules that we use to compile our application. It is very straightforward. There's just a bit of boilerplate to make it the output nicer. So this is the compile target. And finally, down here, we have a so-called the run target, which launches your simulation depending on what kind of platform you choose. So normally what we use is RTL. So RTL will launch the vSim simulation, and it will set up for you a few symlinks. It will set up, it will down here, you can see it will convert your binary into something the simulator can understand. And then finally, it will launch your simulation. Let me show this. So with this kind of elaborate vSim command. So let me recap. So PULP runtime has like a set of makefile fragments, which are ordered in this hierarchical fashion, and depending on what you on what exactly your target is, it will change this makefile. Sorry, the laser pointer is not in.
Yeah, the mouse pointer doesn't match where we point if you do not activate the laser pointer.
Depending on what your environment variables are, it will include a different makefile fragment, and then from there on change all your build rules and your compilation rules. Okay, so normally when you play around with this stuff, you will need to debug your makefile, and there are a few quite easy ways to do this. One I have shown you already. You can just grab your environment You can just grab your environment for interesting variables that is being set. So often it is something you just grab for something PULP and you see what is being set. So you see the PULP SDK home points to our PULP runtime. The PULP RT home points to our PULP runtime. Again, this is a legacy reason because of the PULP SDK. And finally, we see two more variables which are again duplicate because of legacy reason. PULPissimo and PULPissimo. So we know, okay, we are good. Another thing you can do is that you can invoke the GNU make tool with -p. That's what I like to do. -p, when you read the man page of make, you will see it will print the database. Basically, what that means, it will inline all the include statements and show you the final make file that is being used to compile your program. So when I do this, I'm now in a generic hello world. So let me show you, it's just hello world, nothing special. The make file, also nothing special. I can do make -p, and let me pipe it into my pager. And you can see this is the full make file that is being used to compile the program. And you can see when I search for PULPissimo.make, you will see suspected the target file is called PULPissimo.make. I mean, there's more things to explore here. Often like to scroll down, for example, to these rules here to see if everything is okay. Let me show you. So for example, PULP sources. So this is the list of source files that is being compiled. I like to check if like everything looks okay. So if, sometimes you will figure out that the file here is missing and you will get a linker error or compile error or something. Okay, so this is the makefile file of the PULP runtime. So now you should know where to look when something goes wrong. For example, let me say when I unset PULP SDK home and I do make -p to see what exactly I get out, you will see at the top it doesn't find this PULP rt.make, and by this point you should then know that some variable is unset. Yeah, it's not set. Okay, so let's move on now. Let me show you the so now let me show you just a simple hello world and a few features of the scripts we have, and how like the whole flow from simulating, from compiling your RTL, from simulating, and from debugging works like more or less. Okay. So you can see I've listed here a few things. Okay, after this, I have listed a few things like what we need for this part. So I personally have like this directory structure. I made a folder called director training. I put in PULPissimo version 6, put in the PULP runtime version 0.06, and training.sv. So I encourage you that you also set up something like this, because in the later exercise you will need like a setup like this to compile and debug and solve the exercises. Okay. Let me go back to my shell. So you see it's exactly can I? Yes. So you can see it's exactly as I've described. I've PULPissimo, I've the PULP runtime, and SV folder. So the SV folder, we didn't put this in the mail we sent out, because this is now the folder. This is not the repository that contains all the exercises. So maybe for demonstration purposes, let me clone it for you, so you can get it under HDBS github.com PULPtraining.sv. Okay, so you will need this for the later exercises. The other part is that you need the compiler. If you haven't done this already, on GitHub, there are pre-compiled versions of the PULP GCC. So let me show you maybe where you can find them. So when you go to PULP platform, PULP RISC-V, this is the wrong RISC-V, new toolchain, then you will see on the right-hand side here, which I marked, you will see the latest release. And when you use CentOS or Ubuntu 16 or 18, you can just wget like this tar bar here. So what I normally do, I just copy this right-click, copy the link location, and then you go into your shell, you wget it. Okay, I don't do it now, but you should get it here, and then you can unpack it, and you should be ready to go. Okay, so this is the setup requirements. You need PULPissimo, the PULP runtime, and the SV folder with the exercises. Okay, when you clone the PULPissimo, what you need to do is again, this was outlined in the mail, in the preparation mail we sent out, but I will reproduce it here. You will need to clone PULPissimo. You will need to make sure you're on the right version. So go check out git log you should be seeing tag version 6.0.0. And then once you have cloned PULPissimo, you need to call the update IP script. It will fetch all the dependencies of PULPissimo, and then you should be ready to go. So then you have everything cloned, but now if you want to run the actual exercise, you also need to compile the RTL first, and this is just a simple make build in your PULPissimo folder, and a bit of patience, and then the RTL should be compiled. Okay, so this is a setup you need now for the further exercises and for tomorrow too. Okay, so do you have any question for this part here? Did you have trouble setting up? Does it work? Otherwise, I will assume, or maybe we'll see later when you try the exercise. When you have trouble, we can also discuss this there. But it's better that you ask questions now so that we can answer them for everyone.
Or in general, ask questions if you have to. Just interrupt.
Okay. So now what I will do, I will just run the hello world, a small demonstration. So this is like basically just to have it recorded, a fully contained version how to run the hello world, and how you can then look at the information you get from one simulation run, what you can get from it, how you can debug it. Okay, so now what we have again, we have PULPissimo clone, the pub runtime, the ASCII folder PULPissimo is compiled. Now we need to first tell our environment we are using that we want to use the PULPissimo compiled RTL, and we do this. So let me and we do this by sourcing the setup vsim script in PULPissimo. Let me do this. So PULPissimo setup vsim vsim.show. When you look at this file, you will see there's nothing crazy special in there. All it does, it sets the environment variable called vsim path and makes it point into the PULPissimo folder. Again, to check out what it does, you can do an env grep vsim, and you can see, okay, my vsim path is set to something pointing in this PULPissimo/sim folder.
Yeah, you have to be a bit careful about this setup vsim script. I know that, for example, if you're using Z-shell instead of bash, the path will not be correct. So to be on the safe side, always print your vsim path variable and check that it's actually pointing to the sim directory within the root of PULPissimo.
Yes, so if you don't use the CentOS 7 default shell, then you might run into trouble. But yes, as I showed, you can inspect your path, and it should point into the sim folder, which is within PULPissimo. Okay, so this is the first part. Now we told our environment where you can find the simulator. But next, we have to tell our environment about the PULP runtime. And again, this is a simple sourcing of a configuration script. In this case, we source the configuration script in the PULP runtime, in PULP runtime configs. In this case, we have several available, but we need the PULPissimo.shell. Okay, again, I check my environment, looks okay. And finally, we need to tell about the compiler, which we either just downloaded or which we have already installed. So we need to set the variable RISC-V GCC toolchain and point it to our GCC PULP toolchain. In my case, I have it in my home folder under PULP RISC-V. I use the version 1.16, which is the latest release. You have to point it to the 1.16. I think, maybe not. Okay, I mean the other ways to do it is just to extend your path variable and make it point to the compiler. So, for example, in my case, this is not the case. When I do a which RISC-V3210 GCC, it will point to some other RISC-V GCC I use. But I personally have a script prepared, so which sets up the environment for me. I use PULP GCC script, and this makes ensure that I use the PULP GCC. But anyway, there are two ways. Either you set this environment variable or you extend your path, whichever you like more. Okay, this is now the full setup, and we are now ready to run applications with the configured setup. So let me go in the SV folder. In the SV folder, we have several exercises in there, and one is just the folder called hello, and it doesn't do much more than it's just a hello world to test your setup. Then we go in there, and then we do make all and run. Make all compiles your application, make run launches request a simulation for your application. So let us wait quickly. Okay, so we see in our case now the simulation ran through. You can see the hello world was being printed. So this is what our application does. And you also see the status core return value 0. So this is the default Unix return value 0. It means success. You also can see 4 errors. And Manuel also already wrote an email. Some people already asked about this. The errors 4 is a QuestaSim bug of this QuestaSim version, and it tries to compile a few files and it crashes the compiler because it has a bug in there. In the Questa version, this bug is fixed. This bug also doesn't matter because the files that are being compiled are actually not used in PULPissimo. So it's a bit ugly, but it doesn't matter. Okay, so normally when you compile applications, at least me, I don't like this very condensed form of compilation. I like it to have it more verbose to see what happens. And in this case, we have a flag. It's called verbose. So you can set verbose 1, and when you do make all, okay, the target already exists. Let me delete it. So when you do verbose make all, you can see the full command that is being run to compile your program, especially when useful when you need to inspect the march flag and other flags to see if they are set correctly. For example, in this case, you can see we set a macro config IOUART equals 0, so UART is disabled. So this is for debugging the compile flow. For debugging a simulation, after you call make run, you will see in your build folder. Let me go into there. Okay, I have to run it again because I didn't make it clean. So in your build folder, you will see a few files that are being generated by the simulation, and these files should help you with debugging. Okay. So you see a few log files as I promised. For example, in the stdout folder, you can see the stdout of different cores. In our case, the P310 is our fabric controller. And in here you will see, okay, there's a hello world printed out, which we also saw when we ran the command back then. You have in the stdout folder a UART output. So when you run a simulation, you can also capture the UART output In our case, this is empty because we didn't use the UART. We used a simulation printf peripheral. So actually, this is a good point. In our simulation setup, we have some kind of fake std out, which only exists in simulation. And when you write to this fake address, this data is being printed out in the simulation. So that's obviously when you run it on FPGA, you have to make sure that you don't write to this address because this doesn't exist on the FPGA. You have to make sure that you use actually the UART to write to std out. You have to make sure that your std out is actually UART. Okay, so this is the std out stuff. Other points you will see is this trace core 1f0 log. So this trace core log shows you the log of all the executed instructions of your program. So well, let me open this. In here, you can see the execution trace of your program. So what you can see first, at the top, we have like some time, which we can see. We have the number of cycles spent, and we have the program counter, the instruction that is being executed, and the mnemonic. Actually, the indentation is wrong here. It should be something like this. But anyway, the point still stands. So let me adjust this maybe. So, and this log is one of the most useful tools to figure out where your program goes wrong. And let's maybe dive into this a bit. You can see when we start, we'll start at this address here. We'll talk about this later. So this is the boot ROM. Then you will see that we go into a wait for interrupt. So nothing happens. And then we see this long sequence of always the same loop. This is code from the debugger ROM. And finally, much further down, now I scroll to the bottom of this file, you will see we execute some program in 1C000, which is the L2, where we loaded our program in. Now, as you can see, I now could tell you exactly what these things mean because I saw it quite a few times already, but I guess for many people it doesn't make much sense what these addresses mean. So that's where now the PULP trace script comes into play. The PULP trace script, let me show you. We can run this over this log here, and it will help you understand what exactly the things mean by combining these symbolic values with the information that is available in your ELF binary when you compile. Okay, so let me close this file. So what you need to do, we have in the PULP runtime. So let me navigate the PULP runtime. I was talking about the scripts folder where we have this PULP trace script. When you run it, let me show you the help because I don't remember exactly how you launch it. So this PULP trace script, you can provide it with a trace file, which is this log file, which we just looked at, and the ELF file, which was run to produce the trace file. And this PULP trace script will produce then a new trace file that combines both information sources into a more useful, hopefully more useful trace file. So let me do this. I invoke PULP trace. I give it the trace core file, the trace log, and I also need to provide it with the binary. In this case, it is the hello binary. And let me pipe this trace into some file, trace proc log. So we have to wait a bit. Okay, now it's done. So now I have to invoke this PULP trace tool on these two things, and I have produced a new file. So let me open this. It still looks bad. So this is because at the very beginning, this 1A000 is this information from the boot ROM, and the ELF binary which we used, the hello world fn, there's no information about the boot ROM, so there's nothing to be done here. But if we scroll down, so let me grep for main, you can see that down here everything becomes much clearer. instead of, let me show you the comparison. So when you open the trace core 1 log, you can see the difference between the right side and the left side. So what happened is now that we symbolized all the addresses. So this helps you much more when you want to try to debug what exactly happens in your code. And actually, it also helps you to understand the startup process very easily, because you see exactly what happens between start, the very first instruction, after after the debugger handles over the control flow, and between start and main, just down here. So anyway, but this is not the point. I don't want to now talk too much about this, but you can see that this is a very useful tool that helps you like analyze exactly what each of your instructions do, which register are being touched, and which function is being touched and executed. Maybe something also interesting is that here Manuel talked about this before. The way the exit is handled in the test bench is with this exit function here. So what it does, it writes into this register a value, and this register is being constantly polled for a value, and when the value is in there, it will stop the simulation. Because the simulation, the RTL simulation can't really know when the simulation is supposed to be finished, other than like polling this register. So this is also something on the FPGA. It can be handled very similarly. So you can always poke this register to see if your program actually finished. Okay. So this was the so this is the process trace log. So this is a very useful debugging tool. Okay. So I have shown you how to run a simple hello world. Well, you will need to run it anyway next when you want to attempt the exercise. So anyway, let me move on. So maybe a few more points about the PULP runtime. There are a few FPGA specific variables in there. This is mostly because the FPGA version it doesn't have an FLL, so there's certain initialization code that is different. When you grep the PULP runtime for these values, you will see more about it. But mostly, what it does, it just disables certain initialization code. Okay. So now onto the first small demonstration. So what is going on here now is that I show how you integrate a small driver into PULP runtime. By small driver, I mean basically I just show you how to add a few files and how to make them compile and link, how you can use them in your program, and then it's up to you to solve the exercise, which extends this little exercise a bit. Okay. Again, back to my shell. So I'm now in the SV folder where we have our exercises, and I go navigate into the runtime triple driver folder. Now, let me show you the file. Or maybe it's better if I show you the Emacs. I'm an editor. Okay, so this small exercise, it's nothing fancy. So we just demonstrate how you tie together the PULP runtime with your own application. So this is very interesting if you want to write small drivers for the accelerator. You have designed or something like this. So you can see this is just a small C file which you are not supposed to edit. So what we need to do, we need to define macros and functions such that in the end we end up at this point here, so that we get this program returns a 0 instead of a 1 or a miscompilation. So this should show you how to add like header files and function bodies so that you can put it into the PULP runtime. Okay, so let's get started. So first, when I try to compile this here, so it will compile, but when I run it, it will fail. So now, simply because it will end up at this branch here. So we need to edit a few things. Okay, so I navigate into the PULP runtime folder. And so, okay. And let me open on the other side the exercise file. So what we need to do, we need to kind of define this macro so that we end up with this branch, and define then this function so that we don't get a miscompilation. So in the PULP runtime, there are basically two folders you have to look at to add a driver. This is the include folder where your header goes in, and the error folder where driver body goes in. So let me now make a small driver body. I call it my ip.c. And in here, well, for now, I don't add anything. Then next, in the include file, in the include folder, I add a small header for my driver to export basically the symbols. And we call it my ip.h. Okay. Now, obviously, what you normally do, you do some header guard. And in here, since we want to hit this branch on the right-hand side, we define my driver macro. Okay, so this hopefully, when this header file is being included, then we will end up at this point here. What we also need to do now is we need to define this RTMy IP init function so that we can link against it. So let me make this declaration here. It's written wrong. And then I move to the body, to the implementation file, where I just make it an empty function. And what I also need to do is I need to include the header file. Okay, so my hope is now that when I compile and run, that now I get at least to this branch here where it says file my driver macro, right? Because this is what we solved then by then. But actually, this is not yet everything, because when we defined now two files, but we didn't tell PULP runtime that they exist. So what we need to do is we need to go into, in our case, into our PULPissimo make file fragment, and in there we have to tell PULPissimo about this new driver file. You can see here for the FLL there are some files being added, but we add something more now for our my IP driver. So I do PULP sources plus equal my ip.c, and this should be it for the C files. Now for the header files, we also need to change something, because when we look on the right hand side, what we often do, we just include pulp.h. Pulp.h in turn includes all the necessary header files we would need for compiling and running this program. I personally like to include each file I need, but now how it's done is the pulp.h is always like a global include file that includes all the required headers for your platform. So we need also to include to edit this file to also make it include our newly defined header. So let me again, I use here this file search where I just search for the files we have in this folder, and in the include folder we have a pulp.h. There are several more, but this is the interesting one. In here, we this is being included. We tell him about our newly defined header file. Okay. So now, hopefully, when I now change to my shell, when I recompile my program, okay, you can see when we compare it with our source code, we can see now that we printed those two lines here. It linked against this function successfully, and now we are failing with this branch here, fail my auto driver macro. And well, we can also check, other than that it linked this value successfully, I always check like with the nm tool whether the linking, whether the symbol was really properly resolved. In this case, it's obvious because otherwise we will get the link error. But anyway, let me show you. I often go into hello driver and I check the nm file for my new symbol. You can see it is properly defined and linked. Okay, so again, let me recap. I showed you very simply how you add your own small driver body and driver header into the PULP runtime and make it link against your program, against your application. Okay, so now it's your turn. We have a prepared. So we have now exercise. As you saw, I just passed the very first part of this small exercise. There's the other part where you have to define another function and another header and make the program return a successful value. So this is really should not take a long time. This is just meant to make sure that your whole tool chain is set up, that you can talk to the compiler, that you can talk to the simulation, and that you can write, that you can make sure that the things you define in PULP runtime are being used into your program. Okay, I think this should take maybe 20 minutes or up to half an hour. So this is really, I really suggest that you do this because this is when you have this setup once running, then you can really go from there for tomorrow. It's very useful.
So in order for the exercises, the way we want to organize these is as follows. I'm going to open now a couple of Zoom breakout rooms, and you are welcome to join whatever breakout room you prefer. And we will do it as follows. So you, okay, now the rooms should be open. In case you are not able to assign yourself to a breakout room, that probably means you are either using Zoom. I'm not sure whether you can use that feature from a mobile phone, but I'm sure that you need Zoom version 5.3, if I remember correctly, or newer. So if that doesn't work for you, maybe try to update your Zoom client. And we will do it as I just said. You join a breakout room of your choice. We have prepared a Google Docs sheet behind this URL shortener where you can queue yourself. Maybe I will quickly show it to you like this. Maybe let me open that URL myself. Okay. So it's /7nn/LAT. So this is the Google Docs sheet. In case you have a question or need help, please just add a new row in the table over here and write which breakout room you're currently working in and your username. And as soon as we are available, we will try to join that particular breakout room and help you with it. If you cannot access Zoom or use Zoom on the particular computer that you're using to share your screen and show the issue, well, consider this an experimental setup. I prepared a private talk room where you can join with any web browser and share your screen over the web browser. We will keep that one open, although that is, I mean, that private room is open to everyone that has a link, so it won't be a private conversation. Yeah, we'll see also if we have time for it. I prepared some little website where you will find the schematics that I showed about the architecture so far. Won't be as necessary for this exercise as for the exercises that will follow. And we have some little FAQ. We'll see whether we will have the time, the leeway to actually update that ad hoc. But yeah, in case you have a question, maybe try to update that page regularly and see if we were able to maybe already address your issue there. Okay, I guess that's all about that. So we have now 2:15. I'd say we will all meet again in the main Zoom session at 2:45. So in half an hour, right, Robert? Half an hour should be about enough.
I guess.
So at 2:45, we will meet again in the main Zoom call and proceed with the next topic. Are there any open questions on the procedures or questions in general about PULP or the PULP runtime? Okay, I guess then, yeah, enjoy the exercise and yeah, let us know if you have questions.
Header.c, header.h, and yeah, so this is the C part. And we can also generate the documentation. So what is always useful is when you don't want to look on the website, or maybe the website already updated their documentation and it is newer than your tool, you can always use the -doc argument to the rec tool, and it will print out the internal documentation, which is for sure matching the current version of the tool you have, except if you forgot to update something. So this is what you do to check it. So this is Markdown. Sometimes this is not very convenient. So maybe what you can do is you can say, for example, I pipe it into a Markdown file, and then you use pandoc or something like this, pandoc -t, and let's make a PDF out of it, and convert it to a PDF file. I need to type it. Doc PDF. Okay, but I can't open it right now in a shell without X11 forwarding. Okay, so this is the internal documentation. So you don't need don't need to go to the website. And maybe another interesting part is like, how does this system Verilog code look like that is being auto-generated? For that, you have to make sure that you have a folder actually, so the tool doesn't tell you really very well what you need to do, but you need to have a folder. So let me make a folder called SV and invoke the rec tool on it to check the flags. I know it by heart. So it says system Verilog is -R. And I just know that you have to also specify a folder, otherwise it will just fail. Okay, so it's -tsv, and then let's put in timer HJSON. Okay, so now in the SV folder, we see two files being generated. A file called the timerrec package.sv and the timerrec top.sv. And okay, let me open both files. So on the left side, we see the package file. So for each register file you generate, you get a package, and this package basically generates for you system Verilog packed structs that they let you easily access the subfields that you have defined in the timer.hjson. So for example, if I open the timer.hjson, then you can see the mapping. For example, this is the config low rec type, and you can see I have defined here a bit called enable. You see the corresponding bit here, this packed struct, also called enable, and so on. So this is a convenience package for you. And then it generates here on the right side the actual register file. It will have a standardized name derived from your timer.hjson, from the name you put in the timer.hjson, and you're supposed to instantiate this module then into your RTL. So what you have in your RTL is you have an RTL, and for the register that are memory mapped, you can use the recen tool to generate for you this module, and then you need to wire up the input and output interface and the clock and so on to this module. And yes, again, you can see here in this case we use this generic register interface instead of tiling. So if you didn't put on here in the timer HJSON rec, but then it would use the low risk default, which would instantiate for you a tiling interface. Now we will dive into this in more detail in the second day, like how we use this, how we instantiate this, and how we hook it up to our IP, and how we use this then to interface with AXI. But I just want to quickly tell you how it works. The rest of the file is not very interesting, so there's like a lot of auto-generated stuff here. It is very regular, and well, the good thing is hopefully it is correct, so you don't make mistakes like when you write it by hand. Okay, so do you have any questions about this part here from the rec tool, or any specific question about the rec tool, or maybe also concerns or own experiences with this tool? And just go ahead and ask your questions. Okay, so in that case, we can, I guess we can slowly move on to the exercise which I have prepared. I think we will, let me just check if I have forgot something about the exercise. Yes, so the goal of this exercise, so the goal of this exercise will be that we now use this rec tool. With, again, this is a straightforward exercise. You invoke the rec tool, you generate this timer header file. You integrate this timer header file in the PULP runtime, and then we try to run the program that I have provided you in this folder. So in this folder, you will see there's a recen.c file, which basically uses the files you will have, the constants you will have defined. And it will also, it will use the constants you should have generated with the rec tool. And the make file to compile is also provided. One thing you maybe have to take care of is that when you check the output of the tool, so let me show you the output, which I have here on the left side. I mean, you will see that there are references to something called the base address. So this, you will figure out that this macro is not defined by the timer header file, by the auto-generated header file. You have to define it yourself. So when you try to solve this exercise, make sure that you define the timer 0 base address correctly so that it will actually work. Another point is you will find the base address of this timer. You find this in the documentation. The documentation is also in the SW folder. When you check the SW folder, the root of the SW folder, we have put in the PULPissimo datasheet. In there, you'll find the base address, which you can use to solve this exercise. And so this is, once you get this program to run, then there are a few more tasks you can do, but these are mostly exploratory to like see how you play around with the tool, what you can do with it. Okay. So do you have any questions regarding the exercise? Otherwise, we will again proceed as before. There will be breakout rooms, we will be around. And yes, until, I think, what is the time plan we have here? Yeah, so 25 minutes, maybe 30 minutes, we have time to do this exercise, then we'll move on again.
Yeah, we'll start again at 15:35 with the next topic. And yeah, as before, use the Google Docs sheet. Let me just post the link once again to the chat. Use the Google Docs sheet if you need help and cue yourself. I saw at least that one of you had issues accessing the website with the additional material. Did that happen to anyone else, or were most of you able to access the web page with the illustration and FAQs? Anyone else where that didn't work? Okay, seems like for the majority it worked, or the majority is not listening. In that case, let's proceed as before. I will open the breakout rooms again, and you can start with the exercise.
Okay, so this was the recen exercise. I hope I'm not going too fast, but I mean, it's more to show you the capabilities of this tool and how you can the capabilities of this tool and how you can interact with it. So do you have any question regarding the rec tool and how you use it?
Or the exercise it just had.
Or regarding the exercise? Okay, in that case, let's continue. So now the next part, I will talk about the PULPissimo booting process. So I will start by showing like how the booting procedure on PULPissimo works. I will give a crash course on LinkerScript. It's very superficial, but should be enough. And then I will apply the knowledge we know about the boot procedure and about LinkerScript, and show you how PULPissimo, how the boot code in PULPissimo is being compiled, linked, and included into the RTL. So basically, we learn about LinkerScripts, which we'll use on the second day, and we apply this knowledge now to the boot code. So I show the LinkerScript knowledge on the boot code as an example. Okay, so this is how the PULPissimo booting procedure looks like. So when we first we are in reset basically, and then after we leave the reset, after we deassert the reset of the chip, we jump to a hard-coded address of the boot ROM. So this is the boot ROM. You see, this is the address space of the boot ROM, and in this boot ROM, there is some logic in there which will pull the value of the boot select pad. Manuel talked about this earlier in the day. There's a boot select pad which allows you to select the boot mode, and the boot ROM will then try to read this value, and depending on what value is being set, it will change the boot behavior. Currently, there are two boot modes that are controlled by the boot cell value. One mode is when the boot cell is 0. Then we will do a boot from SPI, and in this case, the boot ROM has some small instruction in some code in there which will fetch instructions over quad SPI and write them to our memory. And when it's done, it will jump to some hard-coded entry point. So this is when we have boot cell equals 0. When we have a boot cell equals 1, then the boot ROM will just go into an infinite loop or wait for interrupt, and the RISC-V, or go into the wait for interrupt instruction, the RISC-V instruction. So basically, this is, you can see this is a busy loop, and then it will do nothing. And at this point, you need to connect with the debug module, or it can be already connected, but you need to interact with the debug module, and the debug module then will grab control of the core and will write the ELF binary into the memory and will then jump to the entry point. So this is actually the boot mode that we use in the test bench. So test bench does exactly this. It will set the boot select to 1. Core goes in the busy loop. Debug module will grab control of it and write instructions to the L2, and it will then jump to the given entry point. So these are the boot modes of PULPissimo. There are a few more boot modes, but there are more arcane and they are not really maintained anymore, but you will see this now later. Okay, that's the PULPissimo. Now let me give you a small introduction to linker scripts. So a linker script. So basically, when you compile a program, then you have to deal with instructions and with data. And the compiler, it will group the instructions and the data into sections. And it gives them different names. For example, these are some standard names that always appear. So there is the text section. This is basically these are basically instructions, so machine code instructions. Then you get like the data section, and the compiler will put all the uninitialized variables into the data section. So it will group all the uninitialized variables into something called the data section, more or less. There are some edge cases here. And we have the BSS. So this is a special set of variables, namely the variables which are zero initialized. When you in C, when you declare a variable static in the global scope, then it will be always implicitly zero initialized. And finally, we have the arrow data section. This is read-only data. This section is being produced when you, for example, have a constant string. So when you do a printf with some string, and this string is often put as a constant into your binary. Okay, so the compiler groups your instruction and data in these sections. Now in the linker script, we have to, the linker script now basically defines a set of rules how you map these sections to memory. So this is all it basically does. And yeah, so for that, let me show you an example linker script. So now I'm in the PULPissimo folder, the PULPissimo training folder. I will navigate into the subfolder called boot code. So this is this handles all the PULPissimo boot code story. In there, we see several files. We see a bootcode.c file, a crt0.s file, a link LD, and a make file. These are the relevant files. So the make file is the compilation flow, and the boot code and crt0 are the actual program that then generates the boot ROM. So let's first look into the link LD file. Okay, so this is the link LD file. So you can see, so this is what I just mentioned. This is the linker script. Again, a linker script is responsible for mapping a set of input sections, a set of compiler grouped, a set of sections to memory. Often you'd say that it takes a set of input section and generates like a set of output sections. Okay, so let me go through this file line by line. So first we say what architecture we are talking about, and so on. This is not very interesting. And like you can like to add stuff to the search path for the linker. Also not very interesting. The first interesting section is the memory section. In this memory section, we can declare several different sections, memory sections. So we can say, for example, in our case, we say ROM. We generate a section called ROM, a memory area called ROM, which starts at this address and has this size. And here also we say, we declare a memory area called L2, starting at this address with this size. As you can imagine, the ROM is actually the boot ROM. The L2 is actually the RAM, which we load the program into. Okay, let me scroll down here. So for the first interesting thing we see is like these kind of statements here, where we have a set of sections. Maybe you recognize some, like for example, text, read-only data, BSS, which I talked about. And we have at the top another section name. So how this works is that everything that is grouped in these brackets here is being grouped together. So all these sections on the right-hand side, these are input sections from the compiler. These are grouped together, and they are then mapped to this section name we put here. So you can see, for example, yeah, so you see, for example, most interesting, we have the text section. We map this text section to another section called text. Yeah, group it to a section that called name text. Now you can wonder, where does this go to? So this is being answered by this arrow down here. this arrow says, where do we put it? So we group these sections, input sections together, name it this output section, and we map it to the ROM. So this is the whole magic. And so this is, you see, this statement maps to the ROM. And you, down here, more interesting, you see this statement stack. This maps to L2. So again, as you can imagine, that a stack is something we need to be able to read and write to. So we need to put it not in the ROM, but into some memory we can write to. And in this case, we map it to the L2 memory. And remember, the L2 memory is this here, starting at this address. And we know this address is SRAM. Okay. So this is the gist of, this is the basics. And another thing that is maybe interesting is this dot here that always appears. So this dot here is called the location counter. And basically, what I just said, I said all these sections are grouped together to form this output section, but there is actually more to it. So they will be grouped together in a linear fashion. So first, this section appears at the lowest address. This section appears at the next higher address, and so on. This section appears at the higher address, and so on. And this dot here basically is a shorthand. It's basically a way to say that is the current address which the next section is being added to. And actually, you can play many things with it. For example, you can see here. We say before we do anything, we say we assign to the dot. This command here, it's a very arcane syntax, but basically it says, okay, the location counter needs to be aligned to 4 bytes. This is what it does. And next, what is also interesting is that you can not only constrain the location counter, you can also read from it. So what this statement here does, it defines a variable called _as_text, and it assigns the value dot to it. So actually, and this is useful when you need to generate variables that are only known at link time, or that basically are only known at link time. One such thing is the stack, for example. You can see down here, we define a variable called stack and assign to it the value, which is the current location counter plus 1024. Okay, when we now look into the zrt0.s, you can see that in the zrt0.s here in the top, we refer such a name called stack. And this symbol is being defined by the linker script. So this is how you can interact with the linker script and with from code with the linker script. Okay, and yeah, there's many more things to talk about, but maybe one other point is like, let me go through the actual boot sequence. Yeah, let me actually step through the actual boot sequence. So first, what happens is that, let me check if I have everything. Yeah, so first what happens, we start with the zrt0.s. You can see in the zrt0.s, we have some assembly, and this assembly is mapped to the text section. So what happens, this assembly, the compiler maps it to a section called text. This text section appears in the linker on the right-hand side here, and it will be mapped to this text section here as an output section, and then this goes into the ROM. So this is what happens. And anyway, when you play around a bit and you see that this address that is being produced here, this is always at the same address, and this is then in the risky core, the hard-coded entry point, the hard-coded boot address points to this reset handler here. So yeah, you see it does, so it doesn't do much zrt0.s. So what it does, it basically sets the stack pointer, and then we go to main. So remember, in RISC-V, all the register at the beginning need to be assumed to be uninitialized, And so the first thing we need to do in order to call a function is to have an actually valid stack. And this is what we do here. So we set the stack pointer, we jump to main, and now let me go to the boot code.c. And we scroll down here, the main symbol is actually defined at the very bottom of this boot code.c. So this is where the CRT0 ties together with the boot code.c. So this is the main here. You can see this is just GCC story. You say no return because the function actually never returns, so that it doesn't do weird optimizations. So first, what it does, it calls this boot from other function. And this boot from other function, now you see that there's a lot of legacy things here, but basically you can ignore everything until here, where some register is being polled, and this register is actually the boot cell pad value. And depending on this value, it will enter some boot mode. And the boot mode we are interested in is here called boot abort. And when we look for it, we see what it does. It puts us in an endless loop. So this is the Jtag booting I was talking about. Now, actually, if you look into this file and grep for Jtag, you will see there's actually other modes boot that is called boot from Jtag. So why is that? So this is again, I told you there is more boot modes, but many are not used anymore. And this is one of those. Technically, it still works, but it's not used anymore. This is also a Jtag boot mode, which uses some kind of handshaking. So we used to use this boot mode, and we keep it in because sometimes on the tester, it's also very hard to interact with the RISC-V debug module in the same fashion. And this way, with this other boot mode, it's sometimes easier to handle. But anyway, so this is it basically. Okay, so now what happens when I compile this boot code? So let me maybe go in the boot code. I can just call make, and that's it. We compile the boot code, and you will see it generate several output files. There will be a boot code CD. This is the file we actually use. And you see it is just a list of of binary values. And this is a valid system Verilog, a valid Verilog memory dump. And yeah, so we have a memory model, an RTL memory model in PULPissimo that just does a read mem.h system task and reads this boot code into it. And yeah, basically this is what happens. There's also other outputs. For example, it also generates a system Verilog boot code file, which is like a module you could instantiate, but we don't use this here. So this is generated anyway because this is a more generic flow than we actually use. What is there to talk about? Yes, what I sometimes you can do is you want to look at the sections. Now this is again not specifically related to booting, but just to ELF files. You always like to do maybe what I like to do is do a read ELF. So basically it reads information about the binary generated on the files I have. So let me show you maybe the boot code. And so what you will see is all the things I have talked about, and which you also can see in the linker script. So you see all the sections that are the output sections that you will find in the linker script. There are a few more sections that you didn't see in the linker script defined. This is because this is inserted by GCC. So when you, for example, add the -g flag when compiling, it will insert some debugging information that helps you identify, for example, which value has which name and so on. So this is debugging information inserted by GCC depending on your compile flag. These here, this also, and this one is inserted by the PULP compiler to like provide some information. This is also legacy information. We don't need them really anymore. What is also maybe interesting is that I always check the A flag The A flag means alloc. So when you have an A flag, that means that this will need to be loaded into memory in some fashion. And you can see there's a section which actually we don't really use, is the heap L2 RAM. This is used for SPI booting. And there's the text section which obviously needs to be mapped to memory. So this is where we have the A flag. There are other flags, the executable and the write flag, but we don't care about this really in this setting. And what is also interesting to explore is when you scroll down, you will have a set of symbol. You have your symbol table where you can see each symbol you have defined in your program what kind of value it has. So for example, we can look at the stack, and we know the stack needs to be mapped into L2, and this is true. So it starts with 1C00, so it's mapped into L2. We know, for example, that the boot code story needs to be mapped to ROM, and you see also this is true, it is mapped into ROM. There are many more things you can explore, but basically this is the rough overview. Let me think about if I forgot something. Actually, just for completeness sake, let me tell you that there is I was talking about section all the time, but actually what there's also another concept called segments. But basically, what is actually being loaded into memory is not sections, but segments. A segment is a collection of sections. So this is, but this is not that relevant for us. Yeah, in this specific setting. Okay. Let me think about it. Yeah, I mentioned it before. If you just want to look at the symbols that are being defined, you can also use the NM tool, and there are also some fancy flags that you can use. But basically, I use this often to see like if there is like anything that is not linked, or if there's anything weirdly defined. For example, you see here the stack is a variable that is like, which means it's, I think, I don't remember exactly what this means, but we define it only in the linker script, so it's something deeply. No, I don't remember. Actually, only I would have to read the man pages for this. Okay. So maybe last thing is like this. I was talking about like we generate this boot code.cde file. So where exactly is this being used? I was mentioning it. We call a read a mem.h system very log task to read it into into some RTL model, which is then being presented to the RTL simulation as a ROM. Let me maybe find this. Maybe can give me something from this. Yes, so PULP SoC boot ROM. So it's in the PULP SoC. There is this module called boot ROM. There's a bit more fancy stuff here. Basically, we have an abstraction down here, which selects the correct implementation depending on whether you use an FPGA or an RTL simulation or ASIC synthesis. And when I open it, you can see what it does. So it's very straightforward. Again, you see as a parameter, we get this boot code.cde, and this boot code.cde is read with a system verilog task, as I promised, into a memory, which is here. And then this memory is being presented, to the RTL simulation as a ROM. Okay, So this is, I think these are all the building blocks of the boot ROM. So what I showed you, what the linker script does, what it is for, the concept of input-output sections, how the boot flow in PULPissimo works, and how we can use linker scripts to generate custom layouts to, for example, do boot ROMs or many other things. We will use this information then to change in the second page, to change like the memory layout and to map a certain data and the text section to certain banks. Okay. So are there any questions regarding this section about boot code, linker script, and so on? Okay, in that case, I guess we can we have a break, right? Or we see, yeah, we have a 10-minute break. So let's say until 20 past, and then we will rejoin you, and we will continue now again back. We go back more to the hardware, where we talk about RTL Development Flow, about RTL tools, and so on.
Yes, IP management and how you handle dependencies with PULPissimo and PULP SoC. So yeah, we'll continue at 16:20, so 20 past 4. Okay, so after this quick dive, or not so quick dive into the software world, let's come back to the RTL world, where we have a look at the IP dependency management flow that we are using with PULPissimo. So yeah, like this. So currently, at the moment, we are using a IP dependency management tool called IPApprox, which is a tool written in Python, which transitively resolves the dependency between the IPs and takes care of checking out all of the IPs that PULPissimo uses internally. As we saw before in the morning of this training, PULPissimo and especially PULP SoC consists of many independent repositories, and it's the job of this particular tool, IPApprox, to check out all of the sub-IPs of PULPissimo, and it also takes care of managing the file sets for each independent IP. So you don't have to manually edit long file lists and take care of figuring out where to put all of your source code files in order to have them compiled. So this is what IPApprox is doing for you. So in addition to describing the IP interdependency, it also takes care of generating the elaborate scripts for simulation, ASIC synthesis using Synopsys, or FPGA synthesis using Vivado. At the moment, we are still using this particular tool, this IPApprox tool, but we are on the verge of slowly transitioning to a new tool, which is written in Rust called Bender. However, for this particular training, the support of this tool for the particular flow that PULPissimo encourages with its internal structure is not yet ideal and still needs to be refined a bit more. Also, the porting of PULPissimo's IPs to this new tool is not fully completed as of now, so we still show you how to use the old tool. And in any case, if we transition to the new tool, Bender, which I will talk about for a couple of minutes towards the end of this section, we will still keep the backward compatibility with IPApprox. So ipapux itself is called by two Python scripts in the root directory of PULPissimo. So maybe let me quickly show you what that looks like in the tool. Yeah, it seems like my camera is stuck, so I have to take care of that later. But for the moment, yeah, maybe I can just turn off the overlays, right? Yeah, like this. So you see that in the PULPissimo root directory, you probably already noticed if you dive through the code base yourself that there is this particular folder called IPs. And if you freshly cloned PULPissimo and didn't do anything else yet, this folder will be completely empty. And it is the job of this particular script here, the update IPs script, to check out all of the IPs, and the job of the second script, the generate scripts Python script, to generate all of the tickle files that are necessary in order to compile your SoC with QuestaSim, and for the FPGA port, it also generates the necessary tickle files for Vivado in order to synthesize and implement PULPissimo for the various FPGA boards that we support. So yeah, there is not a lot going on in this script. So it basically is just a Python script that calls a set of library functions from the ipapprox tool. The ipapprox tool is in its own repository and is automatically checked out the first time you actually call the script. So the first time you call the update IP script, let me quickly do that right now. The first time you do this update IPs, which is also described in the README of PULPissimo, it will check out the Python tool, the ipapprox tool in its own directory, in this one in particular, IPs tools. And as soon as it checked out the Python tool, it will just call functions from that ipapprox library, in particular the update IPs function and some save database function. As the last step after updating all of the IPs, it will call the generate scripts file. So that would be this thing over here, which generates the tickle files for all the tools that we currently support. So you see here, it generates tickle files for QuestaSim, for Xilium, another RTL simulator, and as well as the tickle scripts for Vivado for the FPGA synthesis. In case you actually wanted to tape out a PULPissimo-based chip, you would add your own commands at the bottom of this generate scripts file, where you call the particular functions to generate the tickle files, for example, for Synopsys to do the synthesis for you. Well, not do the synthesis, but to generate the tickle files that you can use in your synthesis script to automatically source all your source code files. So let me quickly talk about what the description of ipapprox actually looks like. So a description of an IP using ipapprox. So you basically have up to three different files in every repository that's supposed to be handled by ipapprox. You have one required file, which is the source files.yaml. It's just a normal YAML file, which declares all the RTL source code files for your IP. So all the files that should be compiled in order for your IP to be working. It not only does that, but it also allows you to define preprocessor macros that should be defined for this particular IP. And it also allows to set tool-specific flags to conditionally add or remove certain files from compilation, depending on whether the current tool you're targeting is Synopsys or QuestaSim. This is very useful if you have files that should only be compiled during simulation and files that are only supposed to be compiled during synthesis. So let me open one of these source files.yaml for you so you can get an idea what this actually looks like. So, for example, let me open the source files.yaml in Risky. You see right now I am in the IPs directory that contains the checked out subrepositories of PULPissimo, or the checked out IPs that PULPissimo depends on in a flattened view. So if we open RISC-V, the RISC-V repository, this used to be the repository where the Risky core lived. Nowadays, it's a redirect to the Open Hardware's group's repository to the CV32E40P core, but still using the same version that Risky was before it was moved to the Open Hardware group. So if I open the source file.yaml, we see that it actually doesn't have that much of a complicated structure. You basically have different file sets that you declare with a name. So this is just an identifier that you can choose on your own. And then you have a section where you declare all the files that should be compiled for that particular file set. So for the Risky core, we see that we should compile all of these files in order for it to work. Down here, we declare another file set, the RISC-V verification IP RTL, which adds an additional file that's supposedly only used for verification, this RISC-V tracer.sd file. Besides the file section, we actually see a bunch of other sections that we can add to our file lists. Or we can add an inctiers section, which allows us to specify include directories we need for that particular IP. So these paths we add over here will be added to the include path of that particular IP once we compile it. So yeah, this is quite an important thing. If you're using header files, this is the place where you register the include path, and the Tickle scripts generated by IPAPOX will take care of setting the appropriate include paths for the particular IP. About the vlog opts, I will talk a bit later, but for now, let's focus, for example, on the flex section, which is another optional section that you can add to your file set. The flex sections allows you to add additional flags in order to conditionally include or exclude certain file sets from the Tickle scripts that are generated. I guess the skip synthesis flag is pretty self-explanatory. It just means that everything within that particular file set is not supposed to end up in a Tickle script for synthesis. So you will see this file set in the output for QuestaSim. You won't see it in the Tickle script generated for Synopsys or Vivada, for example. There are other flags. For example, there is also a skip simulation flag that does the reverse thing. It will just remove the file set from anything that's intended for simulation. So this flag should be used to filter the file sets that should end up in the Xcelium or the QuestaSim target, and just allows you to maybe register source files or RTL that might contain technology-specific wrappers that are not intended to end up in the simulation environment. Because in the simulation, you probably have behavioral description of your IP, and for the actual synthesis, you want to use the wrapper that instantiates the actual macro. So SRAM macros or wrapper for SRAM macros would be a good examples, or technology-specific cells that are occasionally manually instantiated in PULP SoC. But we will talk about those later when we go through the PULP IP landscape. So Another pretty, so actually let's talk about the vlog opts right now. So the vlog opts or vlog options section allows you to add additional flags to the vlog command of QuestaSim, which is the compile command of QuestaSim. The way IP-APUX works at the moment is that every IP, or actually I think every file set, if I'm not mistaken, ends up in its own QuestaSim library. So all files in that set will end up in its own library, and the library will be called RISC-V_lib. So something like this ends up in RISC-V_lib. Now there is one particular issue, namely if you try to use a system verilog package from a different IP. The issue is that already during compile time, QuestaSim needs to know where to find this particular package. Module resolution is perfectly fine if that happens during elaboration time. QuestaSim doesn't care if there is a module that it doesn't know about it yet, as long as it will be resolvable during elaboration. But for system verilog packages, that's a different story. There, the package needs to be already defined during synthesis, during compilation, during the vlog step of QuestaSim. Thus, in order to use system verilog packages of a different IP, you need to append a -L flag to the vlog command. This will cause QuestaSim to load the fpnew library before it tries to compile RISC-V. And since the particular package that we are using in the RISC-V core is part of the floating point IP, so fpnew is the floating point IP. In order to use a package within the floating point IP, we need to load this particular library. The dependency resolution scheme will make sure that this particular library will be available before it actually tries to compile the RISC-V core, but still we need to add this -L flag for every IP which contains system verilog packages that we need to use in that particular IP. So maybe to rephrase that, if you're using system verilog packages within your own IP and nowhere else outside, you don't need this at all. However, if RISC-V, for example, uses some package, maybe something like this, import package Oxybus, something like this. I don't know whether that exists, but it doesn't matter. Let's suppose that the RISC-V core internally uses a type or a parameter declared in a package which is part of the Oxy IP. In that case, I would have to add here -L Oxy_lib for it to work. Otherwise, simulation in QuestaSim won't work. For synopsis, synthesis and synopsis, that's a different story. There we don't need it, but for QuestaSim simulation, that's a required step. This is one of the reasons why Bender would be a nicer solution, because it doesn't require that particular step, but for now, that's the way we have to do things. Another important detail is about header files. As you notice here, the first entry in the include path, or in the path that we add to the include paths, is within the IP itself. So if we go through the folder structure, we see that there is a folder called RTL, and within that folder there is an include folder. And this is supposedly the location where files within the RISC-V IP are including system verilog header files from. However, if you look at the second entry, you notice that this is not actually part of the IP itself. So it is actually 2 hierarchy levels above the RISC-V repository in RTL/includes. This is a, I'd say a rather ugly hack in order for the include paths to work. I don't think it's a nice thing that you are specifying dependencies with relative paths outside the actual location of the IP, but that's the way it works right now, and the only way we can make it work if we require header files, which again are not part of our own IP. In that particular case, the reason we need it is that the RISC core requires some variables or some preprocessor macros which are defined in that global include directory of PULPissimo itself. So are there any questions about the structure of the source files.yaml, what it is used for, or general questions that already arise right now about IP approx, or comments about it? No? Well, in that case, I will resume with the next file, which is the ipslist.yaml file, which is an optional file. ipslist.yaml is the YAML file where you declare dependencies. So if your IP is instantiating modules or uses a package from a different IP, the ipslist.yaml would be the location where you declare this dependency. And not only do you declare what particular IP you need, you also declare this version, the exact version that you require it to be used. So maybe let's open the ipslist.yaml of PULPissimo itself. So in the top level directory, we see that there are only two dependencies for PULPissimo. One is PULP SoC and one is tbtools. The reason why there are only two is simple and relates to what I explained in the morning of this training. Most of PULPissimo's IPs and most of PULPissimo in general actually happens in a sub-repository called PULP SoC. So PULPissimo is not the right place to look which IPs are used. If you are actually interested in that, you rather look at the ipslist.yaml within the PULP SoC IP. And if we open that one, we see that there is a lot more going on. So for example, the PULP SoC requires modules or IP from the common cells repository. It requires the APB GPIO IP. It, of course, requires the RISC-V core, so the RISC core, or in case you switch the core that you want to use within PULPissimo with the top level parameter IBEX, and all of the other IPs that PULP SoC uses. The important thing to note is that the dependency is transitive. So PULP SoC only needs to specify the IPs that it directly uses. If one of those IPs by itself has other dependencies, it will have to declare that in its own ipslist.yaml, and ipapprox will take care to build the dependency tree and try to resolve it. It unarguably doesn't do as well of a job as Bender, but in most of our PULP SoC-based tapeouts, it worked pretty well so far, although there are a couple of hiccups that you occasionally have to take care of. So for the IP itself, the important thing to note is that the name that you specify here. So for example, for RISC-V, the name is the repository name. It's not the file list name that we saw in the source files.yaml. Maybe let's open that one briefly, source files.yaml. So you see there are a bunch of different file sets defined for the RISC core. Well, risky is probably a bit of an extreme example. If we have a look at some other source files.yaml, it looks maybe a little bit less confusing. So the common cells IP only has a single file set called common cells all. But the important thing to note is that common cells, so the name you specify here is the name of the repository, not the name of the file sets. The file set name is only relevant to reference the QuestaSim library in case you have to add this vlog options -l flag. And in the IPs list, you specify the repository name. Now, the question is, where does ipapprox actually try to fetch a particular IP? So the default is that ipapprox will take the repository name and generate the following remote. So it will do the very first time it checks out an IP, it will do something like this. It will by default fetch from github.com/pulp platform, which is the default, what is it called in GitHub jargon? I think organization, right? GitHub organization. And it will append the repository name, this one over here, right? To the remote. And of course, it will just clone it first, and then it will try to check out the particular version that you specified with commit. So commit can be any commit-ish reference to a particular well, git commit. It can either be a tag, like in this case. It can be a oops, what am I doing? It can also be a commit hash or even a branch, although I don't recommend using a branch, but it's actually possible to also specify a branch, and then ipapprox will try to keep that branch updated whenever you call the update IPs command up here. So if I call this one, you'll see that it will try now to fetch all of the ipslist.yaml files from the server, and then it will check out all of the IPs you see here. Maybe I have to wait until it stops doing it. Yeah, now it's checking out all of the versions that we specified in here. Okay. And you see that in the very beginning, after the first thing the update IP script does, it will fetch the IPs list.yaml directly from the server. That's an important detail. The IPs list.yaml, if you change it, it will fetch it directly from the server, not from your local file system. So if you change dependencies in sub-IPs, you have to push those changes to GitHub. Now, I said the default is to clone the stuff from GitHub, from the PULP platform organization, but of course, that's not the only possible way to specify where the IP should be fetched from. There is another option, which maybe, where do I have such an example? Maybe here. Okay, so this would be another example of one of my own IPs. So as I said, the default is to fetch from the GitHub server from an organization called PULP platform. But it is actually possible to fetch from an arbitrary Git SSH address by specifying the optional server key. So let's suppose I no longer want to use the common or the micro-DMA core from GitHub, but from some arbitrary repository, Git repository. I would just replace it with git add and then the name of the repository, for example, our own GitLab server, as we already see down below for the other IPs. And the group could be replaced with my own username. And the result would be that all of this ends up with a new remote address of the following form, git. So this results in a git clone from like this. /main/ the actual IP name. .git. So with this style, you're able to specify your own repositories and are not forced to use the GitHub, and not forced to use the PULP platform organization in order to fetch IPs. So this is how you can specify a specific version living on a specific Git server with this remote address here. Are there any questions about specifying IP dependencies using the IPs list.yaml so far? No? Well, in that case, I will just quickly mention the last file that you could add to an IP. Actually, the RTL list.yaml is only useful or only works, if I'm not mistaken, in a top level IP. So, for example, PULPissimo IP. Let me open it. PULPissimo. Like this. So PULPissimo actually has such a file, the RTL list.yaml, and this is more or less the same like the IPs list.yaml, except that it doesn't specify IP location in terms of Git repositories, but in terms of local subdirectories of the IP you're using. I don't want to waste too much time on explaining how that thing works, but just important to know that for PULPissimo, the top level source files are specified in a subdirectory called RTL, and the important one would probably be this one here, which again has its own source files.yaml specifying all the top level source files of PULPissimo. Most of the time, you only need the source files.yaml for your sub IP and IPs list.yaml in case you have dependencies on other IPs. Now, one point that I also want to mention, a more annoying part about working with IP approx is, a general problem of system Verilog, and that is version conflicts. So in case you have IPs that depend on different versions of the same sub IP, let's suppose the Soc Interconnect requires Oxy tag version 1.2 and Risky requires version 1.3. That would be an issue. For IP approx, it would be an issue. The tags I just mentioned are semantic tags, so in theory, it should be compatible because it was a minor version bump from 1.2 to 1.3, but IP approx will only compare whether the exact commit that you specified in your IPs list.yaml. So let's open it again. So IP approx will enforce that all of your IPs in the whole project specify the exact same commit value over here. So you should always make sure that you properly freeze your IP versions and that they always all point to the same version. Otherwise, IPRPOX might start to misbehave. It will try to warn you that there is a version conflict, but I saw in the past that this warning not always worked, and sometimes it will crash. But regardless of that, I mean, in any case, this is an inherent problem of System Verilog. You cannot have different version of the same module in a single project without using some additional tool that does module automatic renaming of modules, because compiling the same module twice, or a System Verilog file containing the same module twice, will automatically override the first version that you compiled. So yeah, you have to take care of this. Okay, so are there questions about IPRPOX? How to use it? I mean, we will have an exercise in a couple of minutes where you will try that yourself and try to integrate your own little dummy IP into PULP SoC, or actually PULPissimo. But yeah, if there are no questions about it right now, maybe they will pop out later during the exercise. I think I explained everything I wanted to show you about the description of an IP with IPRPOX. So yeah, these illustrations, I don't want to go into the details of it. They just visualize what IPRPOX is actually generating with the various calls in the generate script. So this little sketch visualizes the lines you see here in the generate script of Calpisimo training over here. So let's go to the, yeah, that's the part for QuestaSim. So these are the lines that are actually all of those 6 lines. Statements are the ones that will generate the necessary Tcl script and make files for QuestaSim in order to compile the whole PULPissimo project. And this visualization here shows you what exactly each of those function calls will generate and how the outputs of those function calls interact with each other. But yeah, maybe more important when you try to understand how the simulation actually works, or when you want to modify the way that QuestaSim compiles certain things. But yeah, we have the same thing for the FPGA output. Again, there are a number of functions that are called in order to generate the Tcl scripts, and this just visualizes how the outputs interact with each other. Okay, now about development flow. I mean, this is just a recommendation. This is the way I usually do it. By no means is this the right way to do it. It's just the way that I prefer it. There are other ways of development, but yeah, let's anyway show it to you. So in case that you want to do modifications to the top level of your project, for example, PULPissimo, the only thing you have to modify, if you have to modify anything of IPRPOX at all, is the source files.yaml in the RTL directory. So this file over here, RTL PULPissimo source files.yaml. If you add new files to the top level and you want them to be compiled with PULPissimo, this is the location where you add them. If you need new include directories, this is where you add them. So, I mean, adding stuff to the top level is pretty straightforward, and that's not the hard part about using PULPissimo. But in any case, if you modify anything in the source files.yaml. The step that you always have to do after modifying anything in source files.yaml, regardless whether it's in the top level or in a sub IP, is before you run the compilation again with make builds, you have to regenerate the tickle scripts, right? So make builds is just the target that calls QuestaSim and compiles everything. But before you do that, you should always regenerate the tickle scripts for all of your IPs. So with generate scripts, this is what's going to happen. You don't have to always call update IPs. This is only required if you modify dependencies. So if you modify IPslist.yaml files. However, the more involved task most of the time is to modify one of the independent sub-IPs. And the way I usually do that is you modify the IP in the checked out directory in the IPs subdirectory of PULPissimo on a new feature branch. So you create a new branch in the IPs subdirectory. And in all dependent IPs, not in the dependencies, but in the IPs that actually depend on that particular IP, you change the commit in the IPs list dependency to this particular feature branch, just for the moment. It's not, you never should actually tape out or work for a longer of time with feature branches in your dependency version tags, but just for development, it's sometimes easier to work with a feature branch in order not to have to bump all of the commit IDs over and over again in all your sub IPs. Then the next step would be if you add new dependencies to the project, you add them to the right IPs list.yaml file, you commit that particular file, and you push the changes to the server, whatever server that might be. The reason, as I mentioned before, if you call update IPs, it will fetch the IPs list.yaml files from the servers and not from your local file system. So just saving the file in your checked out directory does not have any effect on IP uphooks. Only the source files.yaml are directly read from the file system, but the dependencies are fetched from the server always. After you added the new dependencies to the IPs list.yaml and push those changes, you run update IPs to resolve the newly added dependencies, and calling update IPs will also automatically call the generate script that will generate the new tickle files for simulation and synthesis. In the end, after you finished debugging and modifying your sub IP and your changes are stable, you commit and tag all of your changes to the sub IP in all the, you commit and tag all of the changes you made, you push those changes, and then you modify the version tag. So again, this part over here, I'll show you. So let's suppose, maybe it's easier if I just showed you what I mean. So let's suppose I want to modify something in the FP new IP. So FP new, let me maybe open the top level. That. All right, so let's suppose I want to modify something in the RTL of the FPNU. So let me just do some dummy changes. I rename that particular signal, not that that makes any sense, but Now I am in the position where my Git repository is in an unclean state, like this. And I would, of course, create a new feature branch, do some modifications. Actually, no, add tools. Okay, so now I should be on a feature branch. I can commit my changes. Some changes. And yeah, now if we look at the Git log, we see I just have right now a new branch called do some modifications, and I committed some changes to it. Now that I added those changes, maybe let's also modify the IPslist.yaml of the fpnew. So IPslist.yaml, that's this one over here. So let's say my floating point unit becomes really fancy, and for some reason suddenly it requires the Oxy repository. So let me check which repository is used in PULP SoC. List. So let's require the same version. PULP SoC already uses version 0.24.1, so I use the same version here. And well, domain, we don't really need that. That's only important if you want to have different synthesis scripts for different larger parts of the system, like cluster and SoC. Okay, so now let's make another commit for that one over here. So create a new commit. Oxy, that's 24.1 to dependency. And again, we see I just added a new commit, and well, I probably don't want to commit that right now. I don't want to pollute the GitHub with this stupid little branch here, but let's assume that I pushed those changes to my server right now, in that case GitHub. Now the next step would be to figure out where fpnew is used. So I just use some graphing magic for this one. So -t YAML fpnew. So I see fpnew is used in PULP SoC, and I don't think anywhere else. No. So you see those search results, they are just in the fpnew repository itself. The only place where an IPslist.yaml actually depends on fpnew is PULP SoC. So this is the place where I now change this guy to, what did I call it? Do some modifications was the branch name. Do some modifications. Again, I would create a commit bump version of fpnew to feature branch, and I would push those changes to the server. Of course, on its own feature branch. And after I did all of these steps, I can call update IPs. I don't do that right now because those changes don't make any sense. I can call update IPs. IPAPOX will automatically update the dependencies. It will warn you if there are new conflicts due to your changes. It will check out all of the new IPs that you might have added to the project. In that particular case, it doesn't have to check out anything new because Oxy was already a requirement of PULPissimo from the beginning. But yeah, anyway. And as soon as you called update IPs, you are ready to call make build again to regenerate everything for PULPissimo. You see right now that since I did some modification to the fp-new, it tried to recompile fp-new, the floating point unit, and of course it failed because I guess it will error out because it no longer finds the BZO signal that I stupidly renamed to BZ2._0. Okay, so I think now I'm basically done with that little, not so little introduction to IP-apox. What we are going to do right now is, it's the last exercise part of this tutorial, is to have a little dummy IP integration exercise. So again, I will open breakout rooms so you can do that. And the exercise right now, this particular exercise is not part of the SW repository that we used so far. It lives in its own repository and you find the link right here. Maybe let me quickly add that to the chat as well. Here's the chat window. So HTTPS. Training dummy VIP. I hope that one works. It's the right link. Yeah, looks like it. So under this repository, you find a little dummy verification IP, and your task, as described in the instructions, is to integrate a fork of this dummy VIP into PULPissimo. Actually in the top level of PULP SoC. So yeah, of course I should switch back to you showing you the screen. So yeah, this is the repository of the dummy verification IP. The verification IP doesn't do anything at all. The only thing it does is it uses some features of other IPs and does some things that require you to use some of the features that I explained you about the source files.yaml. For example, one thing that you should do is to add an appropriate flag to the source files.yaml so this verification IP doesn't end up in the synthesis tickle files. It also requires you to add this -L flag for vlog because it uses some system verilog package from another IP. And the way to verify it, whether everything works, is to build and simulate PULPissimo with an application of your choosing. You can just use Hello World, it doesn't matter. And somewhere in the simulation output, actually in the beginning of the simulation output, if everything worked, the verification IP will generate a print statement like this, successfully integrated dummy IP. In case you missed some of the steps, you will see an error message or no message at all if the integration of the IP didn't work. So right now, I'd say we reopen the breakout rooms, and for this particular exercise, I guess, yeah, we'll give a little bit more time, like 30, 40 minutes, maybe 40 minutes. And I guess after this exercise, there are only 1 or 2 more slides, and then we'll call it a day. Are there any questions about the exercise, about IP-apox, or questions in general so far? No? Okay, then let me reopen the breakout rooms. Okay, let's hope that worked. Alrighty. Okay, then same procedure as before. Use the Google Docs sheet to ask for help in case something doesn't work. And yeah, or in case you have general questions that you want to discuss face to face. We will continue with, or we will wrap up the training with a few words on with a few tips on simulation and debugging at, let's say, 17:50, so 10 to 6. Alrighty, let me continue. So I'm aware that the exercise, for those of you that try to solve it, is rather involving and probably wasn't enough time to solve it. But yeah, in case you want to solve it yourself after the training and have questions, just drop us a mail if something doesn't work or you need some support with it. But yeah, I guess for now we'll just continue with the last couple of slides before we wrap it up for today. So as I mentioned before, IPAPOX is a legacy tool that, like PULPissimo itself, grew quite organically. We are transitioning to a new tool called Bender, which is completely written in Rust and has much better documentation, at least now, in the ways that it works. Maybe let me quickly show you what it looks like on its web page. So I think now I should see my screen again. Yep. So Bender is developed by one of our PhD students, Fabian Schuicki, as well as Andreas Kurt and a few other contributors. And this is basically the repository where you find its documentation. It's not as relevant for this training as I wanted it to be, but unfortunately there was not enough time to finish the transition and work out the remaining issues with the flow when we transition to Bender at the moment. But at least, yeah, there is much better documentation on what are the required sections and what they are doing, and the tool is just overall more stable than IPAPOX in what it's doing. But I guess I don't want to lose too much time on that right now, so let's continue with simulation and debug flow. So in order to debug hardware with PULPissimo, and when you do simulation, you are in the unique position that if you develop your own software, you are actually not only able to look at the output of the core, you are also able to look inside the core, since you have access to the source code of everything. Of course, assuming you have access to some RTL simulator like QuestaSim or Tcdm. So right now, I mean, I have prepared some slides that show you how the different tools interact with each other, what the build target actually does, and how it interacts with the tickle script generated by IPAPOX. But honestly, that's just for reference. I probably will post those illustrations to the web page as well. But for the moment, I think it suffices to say that the make build targets that you probably already used and I already showed you before is just building the simulation platform, while the sim target or the make run target, when you invocate your simulation on the QuestaSim simulator, will call vsim. It will store some tickle scripts from the PULPissimo sim path. This is why you have to set the vsim path environment variable over here, and it will start the simulation. What I want to show you right now are just a couple of tips and tricks on how you can simplify your life and you actually want to debug hardware on PULPissimo and want to figure out the root cause of some issues that might pop up in the RTL. So Switch back to this view. So I guess if I remember correctly, so far we always showed you how to invocate a how to start an application on PULPissimo in batch mode or inside the terminal, where you only have the output of the actual simulation. But let me show you how you can do the same thing with the graphical user interface to have a look at the wave window and see the actual signal traces. So let me first source set up my shell in order to do that. So set up shell. So now my environment variable is properly. No, actually it's not, because I'm not using bash, it's set shell. So let me do that manually. It's the wrong path. Export PCM/. Okay, now we go to PULP runtime. As always, we source config/PULPissimo. Okay, this is ready. And final step, we go to SW hello world. We compile our application, and now we call make run as well. However, we append this particular variable, the make variable GUI equals 1, which causes QuestaSim to start in GUI mode instead of batch mode. So let me do that right now. And if everything goes right, let me move that window to the other screen. Actually, not entirely. I'm using QuestaSim 2020, which deprecated some of the VOP flags that our scripts are using, so I quickly have to modify those. Actually, maybe like this. Actually, they are removed. In that case, let me recompile. It. Ah, that's the reason. Yeah, I modified PULPissimo. Well, I think the easiest is to just have a clean copy of it again, without any of my modifications that I did before during the training. So, well, platform. I'm sorry, this is going to take a couple of seconds to complete, especially when I check out all of the sub IPs. And that's already modified the same files over here. Okay, now I have to again modify my pickle files because I'm using a version of QuestaSim that's too new for our setup. We probably should change that in a pull request on the master branch at some point. For now, this should do the trick. Build. And now I should have a clean PULPissimo version once again. Okay, and I probably should modify my vsim path as well. PULPissimo clean. I call it this. Okay. Now let me. Oh, I actually did that in a new shell. Oh, let's do it here. So. Okay. I hope that does the trick. Yes, that looks better. Alrighty. So what I wanted to show you is now I opened the simulation environment in GUI mode in PULPissimo, in QuestaSim, and I mean, the people of you that are already familiar with QuestaSim know that you can now just add signals in the hierarchy from PULPissimo. So this is the top level test bench. It's part of the RTL in RTL. It's part of the source code of the PULPissimo top level that instantiates the device on the test. This is actually PULPissimo. I mean, I can double click it and they'll see this is the top level PULPissimo file. And now I can maybe add all of the pad signals to my wave window like this. Put it over here. And well, maybe let's group it in a new group top level signals. Okay. However, instead of manually adding all of the signals myself that might be interesting, PULPissimo already comes with a number of wave files that allow you to easily add groups of signals of interest. So probably the most interesting one to add is the software.tcl. Or the most interesting tcl file to source is the software.tcl file. So you call do waves software.tcl and you will be greeted with a number of signals over here, which will show you the instruction disassembly of the risky core, the current program counter value, and the current content of your 32 registers in risky, in Tetra registers. There are more of those wave files that might be interesting. One of the more interesting ones is probably the Soc Interconnect Wrapper, which will give you all the signals that go in and out of the Soc Interconnect. So now let's start the simulation and see what that looks like in the wave window. We see up here, if we scroll in a bit, as we said, after the reset, the first address that's executed is the boot address in the boot ROM, this 1A000080. And we see that the very first instruction is a jump and link that jumps to some other address. And we could use the make disassembly target that Robert showed you before to actually relate the execution in QuestaSim with the assembly. So do it like this. S. Here we have the disassembly. And let's go back to the simulation. So this part is still in the boot ROM over here. This is the part where the Jtag where the test bench preloads the memory via Jtag. You see that's all this stuff that's happening over here. Here, for example. This is where the L2 memory and the private banks are preloaded with the actual application. And over here, let's see that over here is where the Jtag RISC-V debug module handed over control to the core. See that over here? Yeah, this is where it hands. Actually, it should be somewhere else. Maybe over here. So as you probably noticed already, this entry point address of all PULP binaries is is 1C008080, and this is where the application actually starts. So if we have a look at the start address in our disassembly, that's over here, right? So this is this particular address, and in case we don't want to look for this part manually, we can just use the search function. That makes it a bit easier. So over here, search for 10. What was it again? So let's just copy paste. It makes it easier like this, and it will immediately jump to the location where our program actually starts. And now we can trace the application. The flow of execution in the hardware, and we can see at every point what's actually happening in all of PULPissimo's components, like the SoC interconnect. For example, we see that the core over here is starting to fetch through the instruction port, while simultaneously occasionally doing some requests on the data port when there's a load and store instruction. And simultaneously, the debug port is, if we scroll out a bit, is occasionally reading some stuff via Jtag. This is what I mentioned before. As soon as the test bench handed over control to the core, it will fetch, or it will pull from this core status register to figure out when the application has ended. Okay, I guess I don't want to show you much more about this. I guess if you have questions, you can ask them later on, but I guess this is pretty much it for today. There is, or it was actually a lot of information, I guess, for some of you. And so the final part, I mean, yeah, with a smiling face, there is a final exercise that you could actually solve if you want to. It is a more involved one, and I consider it not that easy to solve. It actually requires you to do a bit of everything. You have to develop an application using the PULP runtime. So you have some interaction with the PULP runtime driver, namely the driver functions that configure the FLL. So your task will be to change the FLL frequency of the SoC and the peripheral clock domain. And it will also train your debugging skills, because the training files that you again find in the SW repository will require you to copy over some faulty test bench files, and you are supposed to figure out what's going on, why some of the stuff that you're supposed to solve with software alone fails in hardware. Yeah, so if you have questions regarding that part of the exercise, don't hesitate to ask them. I mean, we are still around for a while after we are ending this first part of the PULP training, so it's a bit more or less open-ended. If you want to solve it, stick around and ask questions if you have them. Also, if you still have questions of other natures, or other want to have some support for one of the previous exercises. But for the ones that are leaving us to have dinner right now, the only thing that I still want to get rid of before we call it a day is please take 1 or 2 minutes to go to the feedback form that we prepared and give us some feedback, what we could improve, or what your general impression was on this first part of the PULP training. This is more or less the first time we do this kind of training in front of a larger crowd, and we would really appreciate if you can give us some feedback over here. Other than that, I think that's pretty much pretty much it for today. I will still open the breakout rooms right now for the ones that are willing to stick around. I will keep them open for, yeah, maybe another hour or two. And if you have questions, just ping us. For the other ones, I guess we will see each other, for some of you, again tomorrow, once again at 9:30 in the morning. The second day of the training, just to give a short teaser what we are actually going to do. So this first day was a pretty long one with a lot of information. Tomorrow there will be just a short part on the PULP IP landscape, which might be interesting for many of you, to give a quick overview what kind of IPs we have available at ETH and Unibo, under the PULP platform organization, and which IP might be helpful for you if you develop your own IPs. And we have some further information about the FPGA port of PULPissimo. Other than that, the rest of the day will consist of 2 more involved exercises that will take several hours to complete. We will give a proper, more thorough introduction to both of these exercises. The first one will be the modification of the memory layout of PULPissimo. I guess that's a basic step in case you have your own chip to tape out. You probably want to modify the amount of SRAM in your system, maybe change the banking factor or add an additional SRAM bank. That will be the first exercise, more involved exercise that we are going to do. As part of this exercise, we will of course also have to modify the linker script, so the software works with the modified memory layout as well. However, the second exercise will be the integration of a dummy IP that we prepared using the RecGen tool that Robert showed you in the afternoon today. And it will also be some kind of full stack IP integration exercise. So you will integrate this particular IP with AXI interface. So you will generate a memory mapped interface with RecGen. You will instantiate the proper protocol converter to AXI, so you can communicate with that dummy IP with AXI. You will instantiate it in PULP SoC at the proper place, modifying the SoC interconnect, and the exercise as well as our tutorial will teach you how you have to how you can modify the driver of PULP runtime to auto-generate the hardware abstraction layer using RecGen to interact with the newly integrated dummy IP in PULPissimo with PULP runtime. So how to write the necessary drivers, and then of course the usual debugging to figure out whether your software hardware interaction works as expected. So that's pretty much all of it. Once again, please take the time to give us some brief feedback. It's only 5 or 4 questions. And other than that, I think that's pretty much it. Are there any questions left that you want to have answered right now? No? Well, in that case, I will still open the breakout rooms right now for the people that are willing to or stick around and still want to work on some of the exercises. For the other ones, yeah, I will see hopefully a lot of you again tomorrow at 9:30 in the morning.